Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the quiet archives where stones remember forgotten storms. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. In the beginning, there are no storms as we know them. No thunder rolling across prairies, no hurricane eyes spinning over warm seas, no lightning-splitting purple skies above forests that do not yet exist. The early Earth breathes differently through metal-laden waters and methane-thick air that would poison any modern lung, yet even here, in this alien infancy, the planet begins its first careful documentation. Each tide that retreats leaves its signature in the sand. Each chemical precipitation settles like seasonal snow, building the first thin libraries of deep time. The Archean seas stretch endless and strange, their surfaces reflecting a sun that burns 20% dimmer than today's star. This younger sun casts a bronze light across waters that hold no familiar blue. Instead, these primordial oceans shimmer with green and amber tints, their chemistry more akin to industrial runoff than any sea a modern eye might recognize. Beneath these waters, iron dissolves in concentrations that would rust a modern ship to powder within days. But here, in this oxygen-starved world, the iron simply waits suspended, patient, ready to record the first atmospheric mood swings of a young planet learning to breathe. The continents, such as they are, exist as scattered islands barely rising above the waves. Most of Earth's surface remains oceanic, and in these vast water expanses, the planet's first memory systems begin their slow work. Volcanic vents along mid-ocean ridges pump dissolved metals into the water column, creating chemical soups that would be toxic to any oxygen-breathing organism. Yet these same waters serve as the canvas upon which atmospheric changes will write their stories. Cyanobacteria cluster in shallow bays, their blue-green mats exhaling the universe's first steady breaths of oxygen. These microscopic organisms represent one of life's most revolutionary innovations, the ability to split water molecules and harvest energy directly from sunlight. The gas bubbles upward through water columns that have never known such chemistry. Each molecule of oxygen encounters iron atoms that have floated freely for millions of years. And something remarkable happens. They remember each other from stellar furnaces, from the nuclear hearts of dying stars where both elements first formed. Now they reunite in Earth's primordial seas, creating the planet's first rust. This rusting occurs in patterns as regular as heartbeats, as predictable as breathing. When the tiny organisms bloom in summer warmth, oxygen production surges, and more iron precipitates from solution, falling to the seafloor like chemical snow. When seasons turn cold or nutrients grow scarce, the oxygen drops, and different minerals settle to the bottom silica. Carbonates, sulfides, layer by layer, season by season. These chemical storms create bands of alternating composition, iron-rich and iron-poor, dark and light, recording atmospheric rhythms in stone that will persist for billions of years. The process unfolds with the patience that only geology can muster. Individual bacterial cells live their entire existence in mere days or weeks, yet their collective impact accumulates across millions of generations. Each bloom represents countless trillions of organisms, each producing oxygen molecules that will alter the fundamental chemistry of their world. The sediments accumulate with similar patience. 1,000 years builds a thickness measured in millimeters. Yet within these minute layers, the entire story of atmospheric change finds its voice. Scientists studying these banded iron formations can read oxygen levels from 4 billion years ago as precisely as meteorologists read today's barometric pressure. The stones remember what the atmosphere has forgotten. Each band contains trace elements that reveal not just the presence of oxygen, but its exact concentration, its seasonal fluctuations, its gradual increase over geological time. The iron acts as a chemical thermometer, barometer, and atmospheric composition detector all at once. Only took 3 billion years for oxygen to become abundant enough to matter. Only required the death of countless microbial civilizations to build archives this detailed. Only demanded the patient rusting of entire ocean basins to create libraries that modern minds can finally decipher. In Western Australia, the Pilbara region holds some of Earth's oldest readable stone memories. Here, exposures of banded iron formation stretch across landscapes that seem more Martian than terrestrial red hills and purple ridges carved by wind and time into galleries of deep history. Each band represents not just a season, but a moment when the planet's breathing shifted just enough to change the chemistry of its blood. The formations rise in tilted layers, their edges sharp against desert skies, their surfaces polished by wind into mirrors that reflect light unchanged since the Archean. These stone archives contain stories written in languages that took humans millions of years to learn to read. The spacing of bands reveals orbital cycles, Milankovitch rhythms that governed seasonal intensity across deep time. The thickness of individual layers speaks to the productivity of ancient seas. The mineral composition whispers secrets about atmospheric pressure, ocean temperature, and the complex feedback loops that governed early climate. The mystery remains. Why did these early oxygen producers not simply poison themselves into extinction? Modern organisms would suffocate in the reducing atmosphere of the Archean. Yet somehow, these ancient chemists thrived in conditions that bridged two entirely different planetary states. Perhaps they evolved complex tolerance mechanisms, cellular pumps that could expel the toxic oxygen they produced. Perhaps they lived in chemical gradients that provided refuge from their own metabolic products. Perhaps they existed in symbiotic communities where some organisms consumed the oxygen that others produced. The stones document the results, but keep the biological secrets locked away in crystalline silence. Walking across these ancient formations, the eye traces iron bands that curve and fold like frozen music symphonies of atmospheric chemistry composed across geological time. Each ridge holds millions of years of weather patterns. Each valley contains the compressed memory of seas that evaporated before complex life even dreamed itself into existence. The geological processes that created these formations continue today, though in different forms. Modern iron-rich sediments accumulate in deep ocean basins, in hydrothermal vent fields, in lakes where anaerobic conditions persist. The wind moves differently across these landscapes. It carries red dust from iron formations that were ancient when dinosaurs first walked, when flowering plants first bloomed, when ice first covered the poles. Each grain of this dust contains molecular arrangements formed in Archean seas, atmospheric memories made solid. Stories of forgotten storms written in the language of rust and time. The dust settles on modern surfaces, car windshields, building rooftops. The leaves of contemporary plants carrying messages from a world that existed before oxygen, before ozone, before the blue skies that define our current atmosphere. In these formations, deep time becomes tangible. A hand placed against the rock touches surfaces that witness the great oxygenation event that recorded the planet's first mass extinction, that preserve the chemical signatures of atmospheric revolution. The stones hold steady under that touch, patient as always, continuing their ancient work of documentation. Tomorrow's weather will add new microscopic layers to sediments forming today. Tomorrow's atmospheric chemistry will find its own way into the geological record. The process continues, unhurried, inexorable, adding new chapters to archives that already span billions of years. The early seas do not simply contain iron. They breathe it, exhale it, dream in metallic currents that spiral through water columns untouched by familiar chemistry. These Archean oceans hold iron concentrations thousands of times greater than any modern sea, creating waters that shimmer with an oily, rainbow iridescence when sunlight penetrates their depths. The dissolved metal moves like liquid mercury through these primordial basins, carrying the chemical signature of a planet still exhaling the breath of its violent birth. Beneath the waves, hydrothermal vents pump superheated water into the ocean depths, their black smoker chimneys belching clouds of dissolved minerals into the surrounding sea. These underwater geysers represent the planet's circulatory system, made visible Earth's molten heart, pumping its metallic blood through volcanic arteries into the waiting ocean. The water that emerges from these vents carries temperatures exceeding 400 degrees Celsius, hot enough to melt lead. Yet somehow, life clings to these furnace mouths, feeding on chemicals that would sterilize any modern ecosystem. The iron travels upward through the water column, dissolved in chemical forms that exist nowhere in today's oxidized world. Ferrous iron, the reduced, soluble form, floats freely through these ancient seas like microscopic ghosts of future rust. Each iron atom waits in solution for the chemical trigger that will transform it from invisible passenger to solid precipitate. This trigger comes not from geological processes, but from the metabolic activities of organisms so small they could dance on the head of a pin, yet so numerous they alter the chemistry of entire ocean basins. The bacterial mats that line shallow coastal areas represent Earth's first atmospheric engineers. These colonies of cyanobacteria spread across seafloor sediments like living carpets, their surfaces rippling with primordial currents, their cells working in coordinated silence to split water molecules and release oxygen into waters that have never tasted such chemistry. The process occurs with mechanical precision. Photons strike chlorophyll molecules, electrons flow through biological circuits, water molecules surrender their hydrogen atoms, and oxygen bubbles emerge like tiny balloons rising through metallic seas. Each oxygen molecule becomes a chemical messenger, carrying news of atmospheric revolution to iron atoms that have waited millions of years for this encounter. When oxygen meets iron in these ancient waters, the reaction occurs with the inevitability of gravity. The soluble ferrous iron oxidizes instantly to insoluble ferric compounds, transforming from invisible chemistry to visible precipitation. Rust forms in real time, creating clouds of reddish particles that drift downward through the water column like chemical snow. This precipitation follows seasonal rhythms as regular as modern weather patterns. During periods of intense bacterial productivity triggered by optimal temperatures, nutrient availability, or solar radiation, oxygen production surges, and iron precipitation accelerates. The seafloor receives heavy deposits of iron-rich minerals during these chemical storms. When bacterial activity slows, oxygen levels drop, and different minerals settle from solution silica compounds, calcium carbonates, organic matter from the bacterial mats themselves. The resulting sedimentary layers accumulate with the patience of deep time, each band representing not days or weeks, but centuries or millennia of consistent chemical conditions. The iron-rich layers appear dark red or black, their crystalline structure preserving the exact moment when ancient atmospheric chemistry shifted from reducing to oxidizing. The iron pore layers show lighter colors, grays, whites, pale greens, minerals that formed when oxygen levels dropped, and different chemical processes dominated the seafloor. Modern geologists reading these banded iron formations encounter chemical information preserved with laboratory precision across billions of years. The ratio of ferric to ferrous iron reveals atmospheric oxygen concentrations. The presence of trace minerals indicates ocean temperature, acidity, and the availability of nutrients that fed bacterial blooms. The thickness of individual bands speaks to the duration and intensity of ancient chemical storms, atmospheric events that lasted longer than human civilization has existed. Only took 500 million years to rust away most of the ocean's dissolved iron. Only required the collaborative effort of countless bacterial generations to transform sea chemistry completely. Only needed the patient accumulation of metal oxide snow to create stone libraries that would outlast continents. The formations themselves tell stories that extend beyond simple chemical precipitation. Some bands show evidence of underwater landslides, iron-rich sediments disrupted by seismic activity, and redeposited in chaotic layers that preserve the moment when ancient seafloors shifted. Other sections reveal the signatures of massive volcanic eruptions, their ash layers interrupting the regular banding pattern like geological punctuation marks between chemical sentences. The mystery embedded in these formations centers on timing and coordination. How did bacterial communities across entire ocean basins synchronize their activity to create such regular banding patterns? Modern marine ecosystems show no equivalent coordination across such vast distances. Perhaps ancient ocean currents distributed chemical signals more effectively than modern seas. Perhaps the smaller size of Archean continents created more uniform oceanic conditions. Perhaps bacterial communities possessed communication mechanisms that evolution has since discarded. The stones preserve the results but conceal the biological processes that created such remarkable chemical coordination. In the Hamersley Basin of Western Australia, these formations create landscapes unlike anywhere else on Earth. The exposed bands stretch across hundreds of kilometers, their parallel lines following ancient seafloor contours now tilted vertical by billions of years of geological activity. Each layer represents a chemical storm that swept across ocean basins larger than modern continents, precipitation events that deposited iron-rich sediments over areas that dwarf any contemporary mining operation. The visual effect resembles geological music, made solid rhythmic patterns that speak to atmospheric breathing on timescales that challenge human comprehension. Standing before these exposures, the eye follows individual bands across valley walls and ridgetops, tracing chemical events that occurred when Earth's day lasted only 18 hours, when the moon hung twice as close to the planet as it does today, when the only living things were microscopic and the loudest sound on the planet was wind moving across empty stone. These iron formations represent Earth's first industrial revolution, a transformation of atmospheric and oceanic chemistry more profound than any human activity. The bacteria that drove this revolution worked without conscious intention, yet their collective impact altered the fundamental chemistry of air, water, and stone. They created conditions that would eventually allow more complex life forms to evolve. Yet they also triggered Earth's first mass extinction event as oxygen became toxic to organisms adapted to the previous atmosphere. The sediments continue their accumulation today, though in different chemical forms. Modern iron deposits form in deep ocean trenches, around hydrothermal vents, and in isolated lakes where anaerobic conditions still persist. These contemporary formations add new chapters to the geological record, documenting current atmospheric chemistry with the same patience that characterized their ancient predecessors. Each grain of modern iron-bearing sediment carries forward the tradition established in Archean seas, stones remembering atmospheric storms, minerals documenting the breathing of a living planet. The wind across these ancient formations carries more than dust. It lifts particles that contain the molecular signatures of Earth's first atmospheric revolution, chemical memories encoded in crystal lattices that have remained stable for billions of years. Each grain that settles on modern surfaces brings news from deep time, messages written in the language of rust and precipitation, stories of forgotten storms that transformed a metal-rich ocean into the oxygen-breathing world that would eventually support forests, meadows, and minds capable of reading the chemical poetry preserved in stone. The Great Oxygenation Event unfolds not as a single moment of atmospheric transformation, but as a slow geological exhale that stretches across hundreds of millions of years. The name suggests sudden change, yet the reality moves with the patience of stone formation and continental drift. Oxygen molecules accumulate in the atmosphere grain by grain, breath by breath, each addition representing millions of bacterial generations working in microscopic coordination to alter the fundamental chemistry of air itself. The transition begins subtly, invisibly, in the chemical composition of seawater and sediment. For nearly 1 billion years, cyanobacteria have produced oxygen as a byproduct of photosynthesis, but this revolutionary gas finds itself immediately consumed by the reducing chemistry of early Earth. Iron dissolved in the oceans acts as an enormous chemical sponge, absorbing oxygen molecules as quickly as bacterial metabolism can produce them. Volcanic gases rich in hydrogen sulfide and methane neutralize atmospheric oxygen before it can accumulate to significant concentrations. Yet, gradually, inexorably, the bacterial oxygen production begins to outpace the planet's capacity to consume it. The dissolved iron in the oceans represents a finite resource vast beyond comprehension, but not infinite. As bacterial communities spread across shallow seas and coastal environments, their collective oxygen output grows exponentially. Each successful colony spawns daughter colonies, which spread to new habitats, which produce more oxygen, which encounters less and less dissolved iron available for chemical consumption. The atmosphere begins to taste metal as the last of the oceanic iron precipitates from solution. For millions of years, the planet's breath has carried the chemical signature of reduction methane, hydrogen sulfide, ammonia, compounds that define the respiration of a young world still exhaling its volcanic birth. Now, slowly, oxygen molecules begin to persist in the atmospheric mixture, building concentrations that have never existed in Earth's previous history. This atmospheric revolution proceeds with the violence of rust formation magnified to planetary scale. Oxygen proves toxic to virtually every organism that has evolved in the reducing atmosphere of early Earth. Anaerobic bacteria that have dominated marine ecosystems for billions of years find themselves poisoned by the metabolic waste products of their photosynthetic neighbors. Entire lineages of microorganisms disappear from the fossil record as oxygen concentrations climb beyond their tolerance thresholds. The chemical warfare occurs in real time across ocean basins and continental shelves. Oxygen-producing cyanobacteria create chemical exclusion zones around their colonies, areas where anaerobic organisms cannot survive. These oxygenated waters expand like slow-motion explosions, growing larger with each seasonal bloom, connecting with neighboring zones of oxidation until vast areas of seafloor become uninhabitable for organisms adapted to the previous atmospheric chemistry. Red beds begin to appear in the geological record, terrestrial sediments stained with iron oxides that could only form in the presence of atmospheric oxygen. These rusty sandstones and mudstones represent the planet's first attempts to rust its surface materials, chemical weathering processes that strip iron from bedrock and transform it into the familiar red coloration of oxidized minerals. The very stones begin to breathe oxygen, their surfaces reacting with atmospheric chemistry to create mineral assemblages that would be impossible in a reducing atmosphere. The formations record this transition with remarkable precision. In the Transvaal supergroup of South Africa, sedimentary sequences show the exact moment when atmospheric chemistry shifted from reducing to oxidizing. Below certain stratigraphic horizons, iron-bearing minerals show no signs of oxidation. Above those same horizons, red iron oxides dominate the mineral assemblages. The boundary between these chemical regimes appears sharp as a knife edge when viewed across geological time, yet represents millions of years of gradual atmospheric evolution. Only took 2 billion years for oxygen to become a permanent atmospheric constituent. Only required the extinction of most previously existing life forms to create chemical conditions suitable for more complex organisms. Only demanded the complete restructuring of oceanic and atmospheric chemistry to establish the foundation for eventually complex ecosystems. The paradox of the Great Oxygenation Event lies in its dual nature as both catastrophe and opportunity. The same chemical revolution that poisoned ancient life forms also created conditions necessary for the evolution of more complex cellular organisms. Oxygen, despite its initial toxicity, proves to be an extraordinarily efficient energy source for cellular metabolism. Organisms that develop tolerance to oxygen discover they can extract far more energy from food molecules than their anaerobic predecessors, enabling the evolution of larger, more complex cellular structures. Some bacterial lineages develop sophisticated mechanisms for managing oxygen toxicity, cellular antioxidants, enzyme systems that can neutralize oxygen radicals, membrane structures that regulate oxygen exposure. These evolutionary innovations represent life's first experiments with what would eventually become the biochemical foundation for all complex organisms. The survivors of the oxygen catastrophe become the ancestors of every plant, animal, and fungus that would eventually populate the planet. The atmospheric transformation extends beyond simple chemical composition to affect global climate patterns. Oxygen proves to be a greenhouse gas, though much weaker than the methane it replaces in the atmosphere. As methane concentrations drop and oxygen levels rise, the planet's surface temperature begins a complex dance of warming and cooling that will eventually trigger the first global ice ages. The chemical revolution initiated by bacterial photosynthesis sets in motion climatic changes that will reshape Earth's surface geography for billions of years. The mystery that persists in these formations centers on the speed and coordination of the transition. How did bacterial communities across different ocean basins synchronize their activities sufficiently to drive such a coordinated atmospheric change? Modern ecosystems show no equivalent capacity for global chemical coordination. Perhaps the smaller size of Archean continents created more uniform oceanic conditions that facilitated communication between distant bacterial populations. Perhaps genetic exchange occurred more readily in ancient microbial communities than in modern ecosystems. In the Paleoproterozoic formations of Minnesota's Iron Range, the transition from banded iron formation to red bed deposition appears with startling clarity. The final bands of iron-rich sediment give way abruptly to terrestrial deposits stained with iron oxides, marking the moment when atmospheric oxygen became abundant enough to rust surface materials. Each layer in this transition zone represents a chemical experiment conducted on planetary scale. Atmospheric compositions that existed briefly during the transition from one stable state to another. The wind patterns across these exposures carry chemical information encoded in mineral dust. Particles eroded from Paleoproterozoic red beds contain iron oxide crystals that formed during the Great Oxygenation Event, molecular structures that preserve the exact atmospheric chemistry present 4 billion years ago. Each grain represents a moment when the planet's breath shifted from reducing to oxidizing, when the very air began to rust whatever it touched. Modern atmospheric chemistry bears the permanent signature of this ancient revolution. Every oxygen molecule in today's atmosphere traces its lineage back to bacterial photosynthesis that began billions of years ago. The 21% oxygen concentration that characterizes contemporary air represents a chemical legacy inherited from microbial communities that transformed a reducing planet into an oxidizing world. The stones remember this transformation in molecular detail, preserving the chemical fingerprints of atmospheric revolution in crystalline structures that will outlast the continents themselves. The sediments forming today continue this ancient tradition of atmospheric documentation. Modern red beds accumulate in arid environments where iron-bearing minerals encounter oxygen-rich air, creating new chapters in the geological record of atmospheric chemistry. These contemporary deposits will preserve current atmospheric compositions for future investigation, adding new layers to archives that already span nearly half of Earth's history. The process continues, unhurried and patient. Stones remembering storms, minerals documenting the eternal breathing of a living world. The planet enters its most profound slumber as ice spreads from pole to equator like a slow, crystalline heartbeat, transforming Earth into a marble of white and silver spinning through space. The Snowball Earth episodes represent climate extremes so severe they challenge the imagination, global ice sheets extending into tropical latitudes, ocean surfaces frozen to depths measured in kilometers, temperatures plunging to levels that would make Antarctica seem temperate by comparison. Yet, even in this planetary hibernation, the geological record continues its patient documentation, preserving evidence of these extreme climates in formations that seem to whisper of ancient winter. The ice arrives gradually, almost imperceptibly at first. As global temperatures begin their descent toward the freezing point of seawater, continental glaciers expand from polar regions, grinding across bedrock with the relentless patience of geological time. Ice sheets thicken and spread, reflecting increasing amounts of solar radiation back to space, cooling the planet further in a feedback loop that accelerates with each passing millennium. Snow accumulates in regions where tropical warmth once dominated, building into ice masses that will eventually bury entire mountain ranges beneath crystalline silence. The transition from temperate to frozen world leaves its signature written in stone formations that challenge conventional understanding of climate stability. Glacial deposits appear in sedimentary sequences that show no gradual cooling trend, no intermediate stages between warm and frozen conditions. Instead, the geological record suggests rapid transitions between ice-free and ice-covered states, climatic shifts that occur over thousands rather than millions of years. These formations document atmospheric tipping points, where small changes in greenhouse gas concentrations trigger massive reorganizations of planetary energy balance. Dropstones scattered through marine sediments provide the most compelling evidence of these extreme ice ages. These isolated boulders, some weighing several tons, appear embedded in fine-grained seafloor deposits hundreds of kilometers from any conceivable terrestrial source. The only mechanism capable of transporting such massive rocks across such distances involves icebergs, floating ice sheets that carve from continental glaciers and drift across frozen seas. carrying rocky cargo scraped from distant bedrock. When these icebergs melt, they release their stone passengers onto seafloors where they become incorporated into normal marine sediments. The distribution of these drop stones reveals the extent of ancient ice coverage with remarkable precision in formations from Australia, Namibia, and northern Canada. Drop stones appear in sedimentary sequences that formed at latitudes equivalent to modern tropical regions. These foreign rocks carry magnetic signatures that record the latitude where they originally formed, allowing geologists to trace their transport paths across frozen ocean basins. The evidence indicates ice coverage extending from polar regions to within a few degrees of the equator, transforming Earth's surface into an almost entirely frozen world. The ice sheets that created these drop stones reached thicknesses exceeding 3 kilometers in some regions, ice masses so heavy they depressed the underlying bedrock by hundreds of meters. These continental glaciers moved with inexorable slowness, advancing across landscapes at rates measured in meters per year, yet their cumulative effect reshaped entire continents. Glacial erosion carved valleys deeper than modern river systems, grinding bedrock into flour-fine particles that were transported hundreds of kilometers from their source. Only took perhaps 10,000 years for the ice to spread from polar regions to tropical latitudes. Only required the crossing of a critical threshold in atmospheric greenhouse gas concentrations to trigger runaway cooling. Only demanded the transformation of liquid oceans into solid ice to create climatic conditions more extreme than any experienced in subsequent Earth history. The chemical composition of these glacial deposits reveals atmospheric conditions during the ice ages that seem almost alien by modern standards. Carbon dioxide concentrations dropped to levels barely sufficient to sustain photosynthesis, creating atmospheric chemistry more similar to modern Mars than contemporary Earth. Methane virtually disappeared from the atmosphere as biological processes that produce this greenhouse gas were suppressed by freezing temperatures. The very air became thinner as water vapor, a crucial greenhouse gas, froze out of the atmosphere and accumulated as ice on the planet's surface. Yet life persisted through these extreme conditions, preserved in microscopic fossils found within the glacial deposits themselves. Bacterial communities survived in isolated pockets of liquid water, hot springs heated by geothermal activity, pools of brine too salty to freeze completely, perhaps even in cavities within the ice sheets themselves. These hardy survivors represent some of the most resilient organisms in Earth's history, life forms capable of maintaining metabolic activity at temperatures that would kill most modern organisms within minutes. The mystery embedded in these formations centers on how the planet escaped from such extreme ice ages. Once ice coverage became global, the high reflectivity of snow and ice surfaces should have maintained low temperatures indefinitely, trapping Earth in permanent frozen conditions. Yet, the geological record shows multiple cycles of freezing and thawing, suggesting that some mechanism could overcome the cooling feedback loops that created snowball conditions in the first place. Volcanic activity provides the most likely explanation for these dramatic climate reversals. Even during global ice ages, volcanic eruptions continued to inject carbon dioxide into the atmosphere, gradually rebuilding greenhouse gas concentrations over millions of years. With no liquid water available to weather volcanic rocks and remove carbon dioxide from the atmosphere, greenhouse gases accumulated to concentrations far exceeding modern levels. Eventually, this atmospheric buildup triggered rapid warming that melted the global ice coverage within thousands of years. The geological evidence for these warming episodes appears as cap carbonates limestone formations that directly overlie glacial deposits throughout the world. These carbonate rocks could only form in warm, tropical seas where calcium carbonate precipitation occurs readily. Their presence immediately above glacial sediments indicates dramatic warming following each ice age. Temperature increases so rapid they transformed a frozen planet into a greenhouse world within geological moments. In the Flinders Ranges of South Australia, these transitions appear with startling clarity in exposures that preserve the complete cycle from ice age to greenhouse warming. Glacial tillites, unsorted rock debris deposited directly by ice sheets, give way abruptly to limestone formations that indicate tropical marine conditions. The boundary between these contrasting deposits appears knife-sharp in outcrop, representing one of the most dramatic climatic transitions preserved in Earth's geological record. The wind across these ancient formations carries dust that contains mineral signatures of extreme climatic conditions. Particles eroded from Neoproterozoic glacial deposits include rock fragments that were ground by ice sheets extending into equatorial regions, sediments that preserve the mechanical signature of planetary scale refrigeration. Each grain represents a moment when Earth's climate system pushed beyond the boundaries of stability, when atmospheric chemistry and orbital mechanics combined to create conditions more extreme than any documented in subsequent history. These formations document climate sensitivity on scales that challenge modern understanding of atmospheric stability. The same physical processes that govern contemporary climate operated during these ancient ice ages, yet they produced conditions so extreme they seem to belong to a different planet entirely. The ice sheets that carved these deposits moved according to the same mechanical principles that govern modern glaciers, yet they achieved coverage extending from polar regions to tropical latitudes. The tillites and dropstones continue to yield information about paleoclimatic conditions as analytical techniques become increasingly sophisticated. Isotopic compositions of carbonate minerals within these deposits reveal ocean chemistry during the ice ages. Trace element concentrations indicate atmospheric dust levels and volcanic activity. Even the size distribution of rock fragments provides information about ice flow patterns and the duration of glacial transport. Modern climate systems bear subtle influences from these ancient ice ages. The carbon cycle that regulates contemporary atmospheric chemistry was fundamentally shaped by the extreme conditions documented in these formations. Ocean circulation patterns established during post-ice age warming episodes continue to influence current climate patterns. The very stability of modern climate may depend on lessons learned during these ancient experiments with planetary refrigeration. Atmospheric chemistry tested under conditions that pushed Earth's climate system to its physical limits. In the middle depths of the Cambrian seas, beneath water columns that filter sunlight into soft green twilight, a catastrophic landslide moves with the inevitability of gravity and the finality of geological time. The Burgess Shale Formation captures this moment of underwater avalanche with such exquisite precision that individual organisms become trapped mid-motion, their soft tissues preserved in mineral detail that defies the normal processes of decay and dissolution. This ancient mudslide creates windows into lost worlds, sudden burials that transform living ecosystems into stone libraries of impossible preservation. The underwater landscape of 508 million years ago resembles no modern seafloor. Steep carbonate escarpments rise from abyssal plains like submarine mountain ranges, their surfaces encrusted with bacterial mats and primitive colonial organisms that have no contemporary equivalents. These limestone cliffs represent ancient reef systems built not by corals, but by microorganisms that secreted calcium carbonate in layered mounds reaching hundreds of meters above the surrounding sea floor. The reefs create complex topography, underwater canyons, vertical walls, overhanging ledges that provide diverse habitats for the explosion of life forms that characterizes the Cambrian period. The organisms that inhabit these ancient seas move through water with anatomical designs that seem drawn from dreams rather than evolutionary logic. Five-eyed Opabinia propels itself through the water column using lateral fins while manipulating prey with a flexible proboscis tipped with a grasping claw. Hallucigenia walks across the seafloor on spindly legs, while defensive spines project from its back in arrangements that challenge understanding of bilateral symmetry. Wiwaxia resembles a living pincushion, its body covered with scales and spines that provide protection from predators that hunt with visual systems more complex than those of most modern arthropods. The mudslide that preserves these creatures begins as seismic activity along the base of the carbonate escarpment. Tectonic forces building within the Earth's crust release suddenly, sending shock waves through the overlying water column. The vibrations destabilize massive quantities of fine-grained sediment that have accumulated on the reef slopes, transforming solid seafloor into a fluid mixture of mud and water that flows downslope with devastating efficiency. The turbidity current moves like an underwater avalanche, carrying millions of tons of suspended sediment at velocities exceeding 100 kilometers per hour. This sediment-laden flow possesses enough energy to transport boulders the size of houses across distances measured in tens of kilometers, yet the same turbulent forces that give the current its destructive power also create the oxygen-depleted conditions necessary for exceptional fossil preservation. The thick cloud of suspended particles blocks light penetration and creates an environment so chemically reducing that bacterial decay processes cannot operate effectively. Organisms caught in the path of this sediment flow experience burial so rapid that normal decomposition processes have no time to begin. Soft tissues that would normally decay within days or weeks become entombed in fine-grained sediments that exclude oxygen and preserve cellular details with microscopic fidelity. The burial occurs with such speed that some specimens preserve evidence of their final moments, digestive systems filled with their last meals, muscle tissues contracted in swimming positions, even the delicate gill structures that extracted oxygen from Cambrian seawater. Only took minutes for the turbidity current to bury entire ecosystems beneath meters of fine sediment. Only required the chance alignment of seismic activity, unstable sediment accumulations, and thriving biological communities to create preservation conditions that occur perhaps once every million years. Only demanded the precise chemical environment of rapid oxygen exclusion to transform living organisms into mineral replicas of extraordinary detail. The exceptional preservation extends beyond simple anatomical structures to capture behavioral information that illuminates the ecology of these ancient seas. Trilobite trackways preserved on bedding surfaces reveal how these arthropods moved across the seafloor, their walking patterns indicating complex behaviors including feeding strategies, predator avoidance, and possibly even reproductive activities. Some specimens preserve evidence of predation events frozen in geological time, partially consumed organisms with bite marks that match the feeding apparatus of contemporary predators. The diversity of life forms preserved in the Burgess Shale challenges traditional understanding of evolutionary patterns and body plan development. Many specimens represent experimental designs that have no modern descendants, evolutionary experiments that were terminated by subsequent extinction events or outcompeted by more successful anatomical innovations. These extinct lineages possess combinations of features that seem impossible by modern standards: organisms with 5 eyes, animals with flexible proboscises ending in grasping claws, creatures with protective spines arranged in patterns that defy conventional understanding of predator-prey relationships. The mystery embedded in these formations concerns the extraordinary diversity of body plans that appear simultaneously in the Cambrian fossil record. Modern ecosystems. Despite their complexity, utilize a relatively limited number of basic anatomical designs. Yet the Burgess Shale preserves organisms with morphological innovations that never appear again in subsequent fossil records. This pattern suggests that early animal evolution proceeded through rapid experimentation with anatomical possibilities that would be later constrained by developmental and ecological limitations. The fine-grained sediments that preserve these fossils also capture information about the physical and chemical conditions of Cambrian seas. Trace element concentrations indicate ocean chemistry significantly different from modern seawater, higher levels of dissolved metals, different sulfur isotope ratios, evidence for ocean circulation patterns unlike any contemporary system. The sediments preserve even microscopic organisms, bacteria, algae, and protists that formed the foundation of Cambrian marine food webs. In the quarries of the Canadian Rockies, these formations yield new discoveries with each excavation season. Professional paleontologists and amateur collectors continue to uncover specimens that expand understanding of Cambrian biodiversity and ecosystem structure. Each new fossil represents an individual organism that lived and died 500 million years ago, yet was preserved with such fidelity that scientists can study its anatomical details, feeding mechanisms, and ecological relationships with contemporary organisms. The turbidity currents that created the Burgess Shale represent a type of geological process that continues in modern marine environments. Submarine landslides triggered by earthquakes, volcanic eruptions, or sediment overloading create similar underwater avalanches in contemporary seas. However, the combination of biological diversity, sediment chemistry, and preservation conditions that characterize the Burgess depositional environment represents a unique moment in Earth's history that has never been precisely repeated. The wind across the Burgess outcrops carries particles that contain the molecular signatures of Cambrian seawater, chemical compositions preserved in mineral structures that have remained stable for 500 million years. Each grain of weathered shale contains trace elements that indicate ocean chemistry, atmospheric composition, and climatic conditions during one of the most important episodes in the history of complex life. These formations continue to yield information about the transition from simple to complex ecosystems as analytical techniques become increasingly sophisticated. Isotopic analyses reveal trophic relationships between different species. Trace fossil evidence indicates seafloor chemistry and the behavior of organisms that left no body fossils. Even the orientation of preserved specimens provides information about current directions and the hydrodynamics of the turbidity flows that buried entire communities in geological moments. The exceptional preservation documented in the Burgess Shale represents a standard against which all other fossil localities are measured. The combination of rapid burial, oxygen exclusion, and fine-grained sediments created preservation conditions so extraordinary that soft tissues, eyes, digestive systems, and even muscle fibers remain visible under microscopic examination. These formations preserve not just the anatomical details of individual organisms, but entire ecosystem snapshots that provide unprecedented insights into the structure and function of ancient marine communities. Modern sedimentary environments occasionally achieve similar preservation quality, particularly in submarine settings where turbidity currents bury organisms rapidly in oxygen-depleted sediments. These contemporary examples of exceptional preservation provide natural laboratories for understanding the geological processes that created the Burgess Shale and similar formations throughout Earth's history. The wind patterns of 200 million years ago move with a persistence that stone remembers better than air itself. Their ancient currents preserved in cross-bedded sandstones that curve and sweep like fossilized gusts across landscapes that have long since vanished beneath continental drift and geological time. The Jurassic deserts stretch from horizon to horizon, vast sand seas that dwarf any contemporary desert. Their dunes migrating across supercontinent surfaces under atmospheric circulation patterns driven by a climate system unlike any that has existed since. The sand grains begin their journey as fragments of granite and quartz weathered from mountain ranges whose names have been forgotten by geography and whose peaks have been ground to powder by erosion spanning geological ages. Each grain carries the crystalline memory of its origin trace elements that record the chemistry of source rocks, microscopic inclusions that preserve the pressure and temperature conditions of its formation deep within ancient continental crust. These mineral fragments travel thousands of kilometers from their birthplace, carried by rivers that flow towards seas positioned in configurations that challenge modern understanding of continental arrangement. The dunes themselves move like slow waves across the landscape, their profiles shifting with wind patterns that follow the gravitational dance of celestial mechanics. Trade winds drive sand transport from east to west across the supercontinent Pangaea, creating dune fields that extend for thousands of kilometers in directions that modern compass orientations cannot adequately describe. The atmospheric circulation operates under boundary conditions that no longer exist, continental arrangements that channel wind flow differently, ocean current patterns that redistribute heat according to different geographical constraints, mountain ranges that alter precipitation patterns in ways that have no contemporary analogues. Individual sand grains saltate across dune surfaces in ballistic trajectories that follow the same physical principles governing modern wind transport. Yet the scale and persistence of these ancient aeolian systems exceed anything documented in contemporary deserts. The dunes reach heights measured in hundreds of meters, sand mountains that migrate across the landscape at rates of several meters per year, burying and exposing geological formations in cycles that span millennia. Their internal structure develops through avalanche processes that occur when wind-blown sand accumulates beyond the angle of repose, creating slip faces that preserve the exact orientation of prevailing winds. The crossbedding that develops within these migrating dunes records wind direction with compass precision, each inclined layer representing a moment when sand cascaded down, a dune face oriented perpendicular to the prevailing breeze. The angular relationships between successive crossbed sets document changes in wind patterns, seasonal variations, longer-term climate cycles, and the gradual shift in atmospheric circulation that accompanies continental drift and changing ocean configurations. These sedimentary structures preserve a record of ancient weather patterns more detailed than any contemporary meteorological station. The preservation of these wind patterns requires burial conditions that prevent subsequent erosion or deformation. River floods occasionally inundate the desert margins, depositing thin layers of mud and silt that cap the Aeolian sands and protect them from further wind erosion. Volcanic ash falls provide similar protective covers, their fine particles sealing dune surfaces beneath mineral blankets that will eventually lithify into permanent geological formations. The transition from active sand transport to permanent preservation occurs gradually, as groundwater chemistry alters the mineral composition of sand grains and cements them together with silica precipitated from dissolved quartz. Only took 50 million years for these vast desert systems to migrate completely across the supercontinent. Only required the patient accumulation of wind-blown sediments, grain by grain, to build formations hundreds of meters thick. Only demanded the chance preservation beneath protective sediment caps to transform ephemeral atmospheric patterns into permanent geological archives. The chemical composition of these ancient sandstones reveals atmospheric conditions during their formation that differ significantly from contemporary desert environments. Iron oxide coatings on individual sand grains indicate higher atmospheric oxygen concentrations than exist today. Chemical conditions that promoted more rapid weathering and the development of distinctive red coloration in desert sediments. The absence of certain trace minerals suggests lower atmospheric humidity, even in comparison with modern arid regions. The fauna that inhabited these ancient deserts left trace fossils that illuminate the ecological adaptations necessary for survival in such extreme environments. Reptile trackways preserved on ancient dune surfaces reveal locomotion strategies adapted for sand transport, broad footpads that distributed weight effectively, gait patterns that minimized energy expenditure during movement across loose substrates. Some trackways show evidence of burrowing behavior, organisms that sought refuge from extreme temperatures by excavating shelters in the sand. The mystery preserved in these formations concerns the remarkable uniformity of wind patterns across such vast geographical areas. Modern atmospheric circulation shows considerable variability even across regions much smaller than the ancient desert systems. Yet, the crossbedding orientations in Jurassic sandstones show consistent wind directions across thousands of kilometers, suggesting atmospheric circulation patterns more stable and persistent than any documented in contemporary climate systems. The mineral composition of these sandstones provides information about the source regions that supplied sand to the ancient deserts. Detrital zircon grains preserve radiometric ages that indicate their origin in specific mountain belts, allowing geologists to reconstruct the drainage patterns and sediment transport pathways that fed the desert systems. Some sand grains traveled more than 3,000 kilometers from source to final deposition, carried by river systems and wind patterns that no longer exist. In the Colorado Plateau, these formations create landscapes of extraordinary visual complexity. Slot canyons carved through cross-bedded sandstones reveal the internal architecture of ancient dunes in three-dimensional detail. The preservation quality allows identification of individual storm events, seasonal variations in wind intensity, and longer-term changes in climate patterns. Each exposure represents a cross-section through geological time, revealing the accumulated atmospheric history of millions of years compressed into accessible rock faces. The erosional patterns that shape these sandstone exposures follow the same physical principles that governed their original formation. Wind and water continue to sculpt the lithified dunes, creating natural architectural forms that echo the shapes of their sedimentary origins. Alcoves and arches develop along planes of weakness within the cross-bedded structure, while resistant layers form protective caps that shelter underlying formations from erosion. The trace element chemistry of these ancient sandstones preserves information about global atmospheric circulation and climate patterns during their formation. Rare earth element signatures indicate the provenance of wind-blown dust, while isotopic compositions reveal precipitation patterns and temperature conditions. Even the magnetic orientations of iron-bearing minerals provide information about the ancient magnetic field and the paleolatitude where the sediments accumulated. Modern sand dune systems provide analogs for understanding the formation processes that created these ancient desert deposits. Contemporary Aeolian research in the Sahara, Kalahari, and other major sand seas illuminates the physical mechanisms of dune migration, crossbed development, and the preservation potential of wind-deposited sediments. However, the scale and persistence of ancient desert systems often exceed anything documented in modern environments. The wind patterns preserved in these formations continue to influence contemporary erosional processes. The cross-bedded structure creates planes of weakness that guide modern weathering patterns, while the porosity and permeability characteristics determined by ancient wind transport affect current groundwater flow and mineral precipitation. The angular unconformities and erosional surfaces within these formations record major changes in atmospheric circulation patterns that accompanied continental drift and global climate evolution. These sandstone formations represent archives of atmospheric circulation that extend far beyond the temporal resolution of any other climate proxy. Ice cores provide detailed climate records spanning hundreds of thousands of years, while tree rings document annual variations extending back several millennia. Yet, the cross-bedding in ancient sandstones preserves wind patterns and atmospheric circulation information spanning tens of millions of years, creating climate archives that encompass entire geological periods and major episodes of continental reorganization. The Carboniferous swamp forests breathe in rhythms measured by celestial mechanics, their massive trunks rising like cathedral columns through water that reflects a sky heavy with moisture and atmospheric chemistry, unlike any that has existed since. These ancient wetlands stretch across equatorial regions of the supercontinent Pangaea, creating vast carbon repositories that will eventually compress into the coal seams that power industrial civilization hundreds of millions of years in the future. The trees themselves possess anatomies adapted for permanent flooding, hollow trunks that resist decay in oxygen-poor waters, root systems that extract nutrients from acidic soils, bark structures that permit gas exchange even when submerged. The atmospheric conditions that sustain these wetland forests represent a greenhouse world of extraordinary intensity. Carbon dioxide concentrations exceed modern levels by factors of 5 to 10, creating atmospheric chemistry that drives photosynthesis at rates that saturate the biochemical pathways of contemporary plants. Oxygen levels reach 35% of atmospheric composition concentrations, high enough to support arthropods the size of small automobiles and amphibians that grow to lengths exceeding modern crocodiles. The very air becomes dense with chemical energy, supporting metabolic processes that operate at efficiencies unknown in subsequent geological periods. The trees that dominate these ancient forests belong to lineages that will become extinct before the first dinosaur draws breath. Lepidodendron rises to heights exceeding 30 meters on trunks that show no annual growth rings. Their cellular structure adapted for continuous expansion in climates where seasonal variations remain minimal. Sigillaria develops bark patterns of diamond-shaped scars that mark the attachment points for leaves shed during vertical growth spanning centuries. These plants reproduce through spores rather than seeds, releasing reproductive particles into humid air that ensures their dispersal across vast wetland systems. The water that floods these forests moves with tidal rhythms driven by gravitational forces operating under orbital configurations that no longer exist. The moon hangs closer to Earth than in any subsequent period, creating tidal ranges that exceed modern oceanic systems by substantial margins. Twice-daily tidal cycles flood the forest floors with seawater enriched with dissolved minerals, while twice-daily retreats expose the surface sediments to atmospheric conditions that promote rapid plant growth and organic matter accumulation. The accumulation of organic debris occurs under chemical conditions perfectly suited for carbon preservation. The acidic waters generated by plant decay create environments where bacterial decomposition operates inefficiently, allowing fallen trees and accumulated plant matter to persist far longer than in contemporary wetland systems. Tannins leached from decaying vegetation further inhibit bacterial activity, while the oxygen-poor conditions beneath the water surface prevent the oxidation processes that normally consume organic matter rapidly. Each tidal cycle brings new sediments that bury organic debris beneath mineral layers, creating alternating sequences of plant matter and inorganic sediment that will eventually lithify into coal beds interspersed with shale and sandstone formations. The burial occurs rapidly enough to exclude oxygen from the organic layers, yet gradually enough to permit the slow chemical transformations that convert plant cellulose and lignin into the complex carbon compounds that characterize coal formation. only took 60 million years for these wetland systems to sequester enough atmospheric carbon to lower global CO2 concentrations dramatically. Only required the burial of entire forest ecosystems beneath sedimentary deposits to create carbon repositories that will influence global climate for the remainder of Earth's history. Only demanded the precise coordination of sea level changes, tectonic subsidence, and plant productivity to generate the most extensive coal deposits in the geological record. The cyclic nature of coal formation reflects astronomical forcing mechanisms that govern sea level variations and climate patterns. Milankovitch cycles driven by orbital eccentricity, axial tilt, and precession create periodic changes in solar radiation that translate into alternating episodes of coal formation and marine deposition. When astronomical conditions favor warm, humid climates, the swamp forests expand and carbon accumulation accelerates. When orbital cycles shift toward cooler, drier conditions, sea levels rise, marine conditions replace terrestrial environments, and limestone formation dominates over coal development. The resulting sedimentary sequences preserve detailed records of these astronomical cycles in alternating beds of coal, shale, limestone, and sandstone. Each complete cycle represents approximately 100,000 years of environmental change, while smaller-scale variations record shorter astronomical periods. The thickness and carbon content of individual coal beds indicate the duration and intensity of optimal swamp forest conditions, while the marine sediments between coal layers document the extent and chemistry of oceanic flooding events. The fauna that inhabits these ancient wetlands includes organisms of extraordinary size and anatomical complexity. Arthropleura, a millipede-like arthropod, reaches lengths exceeding 2 meters. Its segmented body armor protecting internal organs that process cellulose with biochemical efficiency unknown in contemporary ecosystems. Meganeura, a dragonfly-like insect with wingspans approaching 70 centimeters, hunts through forest canopies using compound eyes that detect movement with precision enhanced by atmospheric oxygen concentrations that support neural activity at unprecedented levels. The mystery embedded in these formations concerns the mechanisms that maintain such extraordinary productivity and carbon accumulation rates across millions of years. Modern wetland systems, despite comparable climatic conditions, cannot sustain plant growth and organic matter accumulation at rates approaching those documented in Carboniferous coal deposits. Perhaps the absence of efficient wood decay organisms allowed organic matter to persist longer in ancient ecosystems. Perhaps the unique atmospheric chemistry of the Carboniferous period supported biochemical processes that operated more efficiently than contemporary equivalents. The chemical composition of coal beds preserves information about atmospheric conditions, plant physiology, and ecosystem structure during their formation. Sulfur isotope ratios indicate marine influence during coal deposition. Trace element concentrations reveal the mineral composition of ancient soils and the availability of nutrients that supported plant growth. Even the molecular structure of coal contains organic compounds that can be traced to specific plant tissues and biochemical processes. In the Appalachian coal fields, these formations create topographic patterns that reflect the original geography of ancient swamp systems. Valley floors that contain thick coal deposits mark the locations of ancient river channels and wetland depressions, while upland areas preserve thinner coal beds that accumulated in marginal swamp environments. The three-dimensional geometry of coal bodies provides detailed information about the landscape configuration and hydrological patterns that characterized Carboniferous wetland systems. The mining of these coal deposits reveals internal structures that document seasonal and annual variations in plant growth and organic matter accumulation. Some coal beds show layered structures that may represent annual cycles of plant productivity, while others display massive structures that suggest continuous organic matter accumulation without distinct seasonal interruptions. The presence of fossil tree stumps in growth position indicates rapid burial events that preserved entire forest stands in place. The trace fossil content of coal-bearing formations provides evidence for the terrestrial organisms that inhabited these ancient wetlands. Tetrapod trackways preserved in roof shales above coal beds reveal the diversity of amphibians and early reptiles that exploited wetland resources. Plant root systems preserved in underclay formations document soil development and the rhizosphere chemistry that supported forest productivity. Modern peat bogs provide the closest contemporary analogues to Carboniferous coal-forming environments, though they operate under atmospheric and climatic conditions significantly different from those that characterize the ancient wetland systems. Contemporary peat accumulation occurs at rates far below those inferred for Carboniferous coal formation, suggesting that modern wetland systems cannot achieve the productivity and preservation efficiency that characterized ancient swamp forests. The carbon cycle implications of these ancient wetland systems extend far beyond their immediate geological importance. The burial of atmospheric carbon in coal deposits represents one of the most significant carbon sequestration events in Earth's history, permanently removing greenhouse gases from the atmosphere and establishing the foundation for subsequent climate evolution. The eventual oxidation of these coal deposits through natural weathering and human combustion represents the return of Carboniferous atmospheric carbon to modern climate systems. The wind patterns across contemporary coal-bearing landscapes carry particles that contain the molecular signatures of ancient swamp forest chemistry, organic compounds that have survived hundreds of millions of years of burial and diagenesis. Each grain of coal dust represents accumulated plant matter from organisms that photosynthesized under atmospheric conditions more conducive to rapid growth than any that have existed since. These particles carry chemical messages from greenhouse worlds, atmospheric compositions encoded in carbon compounds that preserve the metabolic signatures of ancient forests. The asteroid approaches Earth with the silence of deep space and the inevitability of gravitational mechanics. Its trajectory calculated by celestial forces that have operated unchanged since the formation of the solar system. This mountain of stone and metal, 10 kilometers in diameter, carries the accumulated debris of planetary formation processes that occurred 4.6 billion years ago. Its surface scarred by impacts with smaller bodies during eons of orbital wandering through the asteroid belt between Mars and Jupiter. The approaching object moves at velocities exceeding 20 kilometers per second, its kinetic energy equivalent to billions of nuclear weapons. Yet its arrival will be recorded in geological formations with the precision of a laboratory experiment. The impact occurs at what will eventually become the Yucatan Peninsula. Though the geographical configurations of the late Cretaceous world bear little resemblance to modern continental arrangements. The collision site lies beneath a shallow tropical sea where carbonate sediments accumulate in warm, clear waters that support diverse marine ecosystems. Rudist bivalves build reef structures that rise from the seafloor like underwater cities, their massive shells creating complex habitats for organisms that have no contemporary equivalents. The water depth at the impact site measures approximately 100 meters, shallow enough that the asteroid penetrates the entire water column and strikes the underlying bedrock with undiminished force. The explosion that follows operates on scales that challenge comprehension. The asteroid's kinetic energy converts instantaneously to heat and pressure, vaporizing both the impactor and thousands of cubic kilometers of target rocks within microseconds. Temperatures at the impact site exceed those in stellar interiors, while pressures reach levels that transform familiar minerals into crystalline structures that exist nowhere else on Earth's surface. The initial fireball expands outward at velocities approaching the speed of sound. creating a hemispheric dome of superheated plasma that rises into the stratosphere within minutes of impact. The shock wave that propagates outward from the impact site travels through solid rock faster than seismic waves from the most powerful earthquakes. This pressure pulse fractures bedrock to depths measured in kilometers, creating networks of impact-related faults that extend hundreds of kilometers from ground zero. The mechanical energy of the shock wave exceeds the total seismic energy released by all earthquakes in recorded human history. Yet this enormous force represents only a fraction of the total energy released during the impact event. The ejector blanket that forms during the impact contains material launched from the crater at velocities exceeding escape velocity. Rock fragments that follow ballistic trajectories extending thousands of kilometers from the impact site. Some of this debris achieves orbital velocities, circling the planet multiple times before re-entering the atmosphere and heating to incandescence during their return to Earth's surface. The larger ejector blocks travel on suborbital trajectories that carry them across continents and ocean basins, distributing impact-related debris across the entire surface of the planet. The atmospheric effects of the impact begin within hours and persist for years following the collision. The superheated ejector that rains back to Earth's surface radiates enough thermal energy to ignite global wildfires, transforming forests and grasslands into ash and charcoal within days of the impact. The fine dust and soot particles injected into the stratosphere create an opaque atmospheric layer that blocks solar radiation for months, triggering global cooling and the collapse of photosynthetic ecosystems worldwide. Only took minutes for the impact to excavate a crater 150 kilometers in diameter. Only required hours for the ejector fallout to circle the globe and begin the thermal pulse that ignited continental-scale wildfires. Only demanded months of blocked sunlight to trigger ecosystem collapse and mass extinction on a planetary scale. The geological formations that preserve evidence of this impact event to you appear as a thin clay layer sandwiched between Cretaceous and Paleogene sedimentary rocks at locations worldwide. This boundary clay contains concentrations of iridium hundreds of times greater than normal crustal abundances, chemical evidence for the extraterrestrial origin of the impact debris. The iridium anomaly appears at precisely the same stratigraphic level that marks the extinction of non-avian dinosaurs, ammonites, and numerous other groups of organisms that had dominated Mesozoic ecosystems for millions of years. The sedimentary structures within impact-related deposits reveal the sequence of events that followed the collision with remarkable detail. Spherule beds contain millimeter-sized glass beads that formed when impact-generated rock vapor condensed in the upper atmosphere and fell back to Earth's surface like a rain of molten droplets. These spherules preserve evidence of their formation temperatures and cooling rates, providing direct information about the physical conditions that existed during the impact fireball expansion. Tsunami deposits associated with the impact event appear in sedimentary sequences throughout the Gulf of Mexico and Caribbean region, massive sand and gravel beds that document wave heights exceeding 100 meters. These marine deposits contain a chaotic mixture of shallow water and deep water organisms, evidence for the complete disruption of normal marine environments by impact-generated tsunamis. The deposits extend hundreds of kilometers inland from contemporary coastlines, indicating that the waves penetrated deep into continental interiors. The mystery embedded in these impact deposits concerns the precise mechanisms that link the collision event to global mass extinction. While the immediate effects of the impact were clearly catastrophic, the pathways through which these effects propagated through global ecosystems remain subjects of ongoing scientific investigation. Perhaps the combination of thermal pulse, atmospheric darkening, and acid rain created conditions that no large organisms could survive. Perhaps the collapse of primary productivity triggered cascading extinctions throughout food webs worldwide. The shocked mineral assemblages within impact breccias provide information about the extreme pressure and temperature conditions that existed during crater formation. Quartz grains show distinctive planar deformation features that form only under shock pressures exceeding those generated by volcanic explosions or tectonic processes. Diamond crystals appear within the impact deposits, formed from carbon-bearing target rocks subjected to pressures that exist nowhere else in Earth's crustal environment. In exposures along the Brazos River in Texas, the impact-related sedimentary sequence preserves a complete record of events spanning the hours and days following the collision. The basal layer contains impact spherules and shocked minerals that fell from the impact fireball. Overlying beds document the arrival of tsunami waves that transported marine organisms and sediments far inland from their normal habitats. The uppermost layers contain charcoal and soot particles from the global wildfires that followed the thermal pulse. The crater structure itself, now buried beneath younger sediments, reveals information about impact mechanics and target rock properties through geophysical surveys and drilling projects. The central peak ring formed when target rocks rebounded from the temporary cavity created by the impact explosion. The terraced crater walls document the gravitational collapse that followed the initial excavation. Even the pattern of radial fractures extending outward from the crater provides information about the stress field generated by the impact shockwave. The chemical composition of impact-related sediments preserves evidence for the atmospheric and oceanic chemistry changes that followed the collision. Soot particles indicate the extent and intensity of global wildfires. Sulfur-bearing minerals document the injection of sulfuric acid aerosols into the stratosphere. Even the carbon isotope ratios in boundary sediments reflect the collapse of photosynthetic productivity and the oxidation of organic matter in global fires. Modern impact craters provide analogues for understanding the formation processes that created the Chicxulub structure. Though none approaches the size and energy scale of the end Cretaceous impact, contemporary meteor crater research illuminates the physics of hypervelocity, impacts, and the geological processes that modify crater structures over time. However, the biological effects of large impacts remain largely theoretical, based on extrapolation from smaller events and computer modeling of atmospheric and climatic consequences. The wind patterns across contemporary exposures of the impact boundary carry particles that contain the chemical signatures of extraterrestrial material. Trace elements and isotopic compositions that originated in the asteroid belt billions of years ago. Each grain of boundary clay represents a moment when Earth's biological history pivoted from one evolutionary trajectory to another, when the impact of cosmic debris redirected the course of life on a planetary scale. These formations continue to yield information about impact processes and extinction mechanisms as analytical techniques become increasingly sophisticated. Isotopic analyses reveal the timing and duration of environmental changes following the impact. Trace element studies provide information about the composition and origin of the impacting body. Even the magnetic properties of impact-related sediments document the intensity and orientation of shock-generated magnetic fields that accompanied the collision event. The ice sheets arrive with the patient inevitability of orbital mechanics. Their advance measured not in seasons or human lifetimes, but in the slow celestial dance that governs Earth's relationship with solar radiation across cycles spanning tens of thousands of years. During the Pleistocene epoch, these glacial masses expand from polar regions like crystalline heartbeats pulsing across continents, their forward edges grinding across landscapes with forces that reshape geography on scales that dwarf any contemporary geological process. The ice accumulates grain by grain, snowfall by snowfall, building thickness measured in kilometers and extending coverage across millions of square kilometers of continental surface. The Laurentide ice sheet spreads southward from Hudson Bay like a frozen ocean, covering most of what will eventually become Canada and the northern United States. Its southern margin reaching latitudes where temperate forests now flourish. This continental glacier contains enough frozen water to lower global sea level by more than 100 meters, exposing land bridges that connect continents and creating migration corridors that will funnel organisms between previously isolated biogeographical provinces. The ice moves with mechanical persistence, advancing at rates measured in meters per year. Yet its cumulative effect transforms entire continental surfaces into landscapes that resemble modern Antarctica. The grinding motion of ice against bedrock operates through processes that combine the patience of geological time with forces that exceed those generated by any other surface phenomenon. Individual ice crystals, each initially the size of snowflakes, recrystallize under pressure into solid masses that flow like viscous liquids across topographic obstacles. The basal ice, pressurized by the weight of overlying glacial mass, reaches temperatures approaching the melting point, creating lubricating water films that facilitate sliding across underlying rock surfaces. The erosional power of moving ice exceeds that of rivers, wind, or waves by orders of magnitude. Glacial abrasion polishes bedrock surfaces to mirror-like smoothness, while simultaneously carving deep scratches that preserve the exact direction of ice movement with compass precision. These glacial striations appear as parallel grooves carved into solid rock, their orientations indicating ice flow patterns across continental surfaces. The striations range from hairline scratches created by fine sand particles to channels several centimeters deep, gouged by larger rock fragments embedded in the basal ice. The transport capacity of continental ice sheets allows them to carry enormous quantities of rock debris across distances measured in hundreds of kilometers. Boulders weighing several tons travel from their source outcrops to deposition sites where geological context provides no explanation for their presence except glacial transport. These erratic blocks, composed of distinctive rock types that can be traced to specific source regions, document ice flow patterns and the extent of glacial coverage with greater precision than any other geological evidence. The landscapes that emerge from beneath retreating ice sheets preserve detailed records of glacial processes in landforms that persist for tens of thousands of years after deglaciation. Drumlin fields contain thousands of elongated hills sculpted by moving ice, their orientations aligned with ancient ice flow directions, their asymmetric profiles recording the mechanical interaction between flowing ice and underlying sediments. Esca systems trace the paths of subglacial rivers, sinuous ridges of sand and gravel that mark the locations where meltwater streams flowed beneath hundreds of meters of glacial ice. Only took 100,000 years for ice sheets to advance from polar regions to temperate latitudes. Only required the slow orbital forcing of Milankovitch cycles to trigger glacial expansion that covered 1/3 of all continental surfaces. Only demanded the mechanical persistence of flowing ice to carve valleys deeper than modern river systems and transport rocky debris across entire continents. The moraines that mark former ice sheet margins appear as irregular ridges of unsorted rock debris, chaotic mixtures of clay, sand, gravel, and boulders that accumulated along glacial fronts during periods of ice sheet stability. Terminal moraines document the maximum extent of glacial advance, while recessional moraines record temporary halts during overall retreat. The composition of morainic debris reveals information about the bedrock geology across vast areas of ice sheet coverage. Rock types mixed together from sources separated by hundreds of kilometers. The chronology of glacial advance and retreat emerges from radiocarbon dating of organic materials found within glacial deposits and from the analysis of oxygen isotope ratios in deep-sea sediment cores. These records reveal that major glaciations occurred approximately every 100,000 years during the late Pleistocene, with shorter warm periods separating longer cold episodes. The timing of these glacial cycles corresponds precisely with orbital variations that affect the amount and seasonal distribution of solar radiation reaching Earth's surface. The mystery preserved in glacial landscapes concerns the mechanisms that triggered rapid transitions between glacial and interglacial conditions. Ice sheet models indicate that gradual orbital forcing should produce gradual climate changes, yet geological evidence suggests that major glacial advances and retreats occurred within centuries or millennia rather than tens of thousands of years. Perhaps feedback mechanisms involving ocean circulation, atmospheric greenhouse gas concentrations, or ice sheet dynamics created threshold effects that amplified small orbital changes into dramatic climate transitions. The lakes that formed along glacial margins preserve detailed records of ice sheet behavior and environmental conditions during glaciation. Glacial Lake Missoula, impounded by an ice dam across the Clark Fork River, contained volumes of water equivalent to modern Lake Erie and Lake Ontario combined. The catastrophic failure of this ice dam released floodwaters that carved the channeled scablands of eastern Washington, creating landscapes that preserve evidence for flood discharges exceeding those of all modern rivers combined. In the Canadian Shield, glacial landscapes preserve evidence for multiple ice sheet advances separated by interglacial periods when temperate climates return to high latitudes. Weathering profiles developed on glacial deposits indicate the duration and intensity of interglacial warming episodes. Paleosol horizons buried beneath younger glacial sediments document soil formation processes that occurred during ice-free intervals lasting tens of thousands of years. The extent of glacial coverage determined patterns of plant and animal migration that influenced the biogeographical distribution of species across continents. Ice-free corridors that remained open during glacial maxima served as migration routes for organisms moving between previously connected habitats. Glacial refugia in unglaciated areas preserved populations of temperate species that recolonized deglaciated landscapes as ice sheets retreated. The mechanical effects of glacial loading depressed continental crust by hundreds of meters, creating basins that filled with glacial lakes during deglaciation. The subsequent rebound of crust following ice sheet retreat continues today in areas that were covered by the thickest ice, producing measurable rates of land surface elevation change that exceed those caused by tectonic processes in most continental regions. Modern glacial systems provide analogues for understanding the processes that created Pleistocene ice sheets, though contemporary ice masses operate under climatic conditions significantly different from those that characterized glacial maxima. Ice sheet modeling studies use modern glacial observations to test theories about ice sheet dynamics, basal processes, and the response of ice masses to climate forcing. The atmospheric effects of continental ice sheets extended far beyond the areas covered by ice itself. The high albedo of ice surfaces reflected solar radiation back to space, reinforcing cooling trends and maintaining low temperatures across broad continental regions. The topographic effects of ice sheet thickness altered atmospheric circulation patterns, creating regional climate anomalies that affected precipitation and temperature distributions across entire continents. The wind patterns across contemporary glacial landscapes carry particles that contain the chemical signatures of glacial processes: rock flour ground by ice sheet abrasion and transported by glacial meltwater streams. Each grain represents mechanical work performed by moving ice, bedrock pulverized by glacial grinding and distributed across landscapes far from its source. These particles preserve isotopic signatures that indicate their origin in specific bedrock formations, providing traces for glacial transport pathways. The hydrological effects of glacial meltwater created river systems that operated under discharge regimes unlike any documented in contemporary environments. Glacial outburst floods from ice-dammed lakes generated peak discharges that exceeded modern river floods by factors of hundreds or thousands. These mega floods carved canyon systems in matters of days or weeks, creating erosional landscapes that normally require millions of years to develop. Modern climate systems continue to respond to the effects of Pleistocene glaciation through mechanisms that operate on millennial timescales. Ocean circulation patterns established during deglaciation continue to influence current climate distributions. Crustal rebound from glacial unloading affects contemporary rates of relative sea level change. Even the distribution of continental ice masses during glacial maxima influence the development of soil profiles and vegetation patterns that characterize modern landscapes. The volcanic eruption begins in silence, deep beneath the Earth's surface where magma chambers accumulate the pressurized fury of geological time, their molten contents enriched with dissolved gases that will eventually drive explosive violence on scales that dwarf any surface phenomenon. The Toba eruption of 74,000 years ago represents one of the most catastrophic volcanic events in recent geological history, an explosion that ejects more than 2,800 cubic kilometers of magma into the atmosphere, enough material to bury the entire state of Rhode Island beneath a layer of volcanic debris several kilometers thick. The eruption column rises through the stratosphere like a geological rocket, carrying superheated ash and gas to altitudes exceeding 30 kilometers above sea level. At these heights, the volcanic plume encounters atmospheric conditions unlike those at Earth's surface temperatures that would freeze exposed skin within seconds, pressures lower than those on the surface of Mars, wind patterns driven by the planet's rotation rather than surface heating. The eruption column spreads laterally at the tropopause, creating an umbrella-shaped cloud that extends hundreds of kilometers from the volcanic source. The ash particles that fall from this stratospheric cloud possess sizes and compositions that determine their atmospheric residence time and global distribution patterns. The finest particles, measuring less than 1 micrometer in diameter, remain suspended in the stratosphere for years following the eruption, circling the globe multiple times before gravitational settling finally brings them back to Earth's surface. These microscopic glass shards carry the chemical fingerprint of their magmatic source, trace element compositions that allow geologists to identify Toba ash in sedimentary deposits worldwide. The atmospheric loading of volcanic aerosols creates global climate effects that persist for decades following the eruption. Sulfur dioxide gas injected into the stratosphere combines with water vapor to form sulfuric acid droplets that reflect solar radiation back to space, reducing the amount of energy reaching Earth's surface. Global average temperatures drop by several degrees Celsius, triggering crop failures, ecosystem disruption, and climatic conditions that approach those of nuclear winter scenarios postulated by atmospheric scientists. The ash fall from the Toba eruption creates deposits that range from several meters thick near the volcanic source to millimeter-scale layers at sites thousands of kilometers distant. These ash beds, now preserved as distinct horizons within sedimentary sequences, serve as precise time markers that allow geologists to correlate rock formations across vast geographical areas. The instantaneous nature of ash deposition means that sediments above and below volcanic ash layers were deposited before and after the eruption, providing chronological frameworks with temporal resolution measured in days rather than thousands of years. The distribution pattern of Toba ash reveals atmospheric circulation patterns that operated 74,000 years ago. wind systems that transported volcanic debris across ocean basins and continental masses according to the same physical principles that govern modern atmospheric dynamics. Ash thickness measurements from sites across South and Southeast Asia document the primary dispersal pattern driven by stratospheric winds, while trace amounts of toba ash identified in ice cores from Greenland and Antarctica indicate that volcanic debris circled the globe multiple times before final deposition, only took hours for the eruption column to reach maximum height and begin global ash dispersal, only required days for volcanic debris to circle the Earth and begin affecting global atmospheric chemistry, only demanded years of atmospheric residence time for volcanic aerosols to create climate effects that influenced ecosystems worldwide. The tephrochronology that emerges from studying these volcanic ash deposits provides one of the most precise dating methods available to geologists and archaeologists. Each major explosive eruption creates a unique chemical signature preserved in volcanic glass, trace element, and isotopic compositions that serve as fingerprints for correlating ash deposits across broad geographical areas. The temporal precision of these volcanic time markers often exceeds that of radiocarbon dating, particularly for events that occurred beyond the range of organic preservation. The human populations that inhabited South and Southeast Asia during the Toba eruption experienced environmental catastrophe on scales that challenge comprehension. Archaeological evidence suggests that human populations declined dramatically following the eruption, creating genetic bottlenecks that may have influenced the subsequent evolution and migration patterns of early modern humans. The ash deposits that buried human settlements preserve snapshots of late Pleistocene cultural development, artifact assemblages sealed beneath volcanic debris that provide insights into human adaptation strategies during periods of environmental crisis. The mystery embedded in these volcanic deposits concerns the precise mechanisms through which explosive eruptions affect global climate and ecosystem stability. While the immediate atmospheric effects of major eruptions are well documented, the pathways through which these effects propagate through global environmental systems remain subjects of ongoing research. Perhaps the combination of atmospheric cooling, acid rain, and reduced solar radiation created conditions that disrupted photosynthetic productivity worldwide. Perhaps the timing of eruptions relative to seasonal cycles determined their impact on agricultural systems and human populations. The magma chamber processes that led to the Toba eruption operated over timescales spanning hundreds of thousands of years, gradual accumulation and differentiation of silicic melts that eventually achieved the volatile saturation necessary for catastrophic explosive eruption. The chemical evolution of these magma chambers can be traced through the composition of volcanic products, crystal assemblages, and glass chemistry that record pressure, temperature, and compositional changes during magma storage and eruption. In the Lake Toba region of Sumatra, the volcanic caldera formed by the eruption creates a landscape that preserves evidence for the magnitude and violence of the explosive event. The caldera structure, measuring approximately 100 kilometers in its longest dimension, represents the collapse feature that formed when the underlying magma chamber emptied during the eruption. The volume of this depression approximates the volume of magma ejected during the explosive event, providing direct evidence for the scale of material removal from the Earth's crust. The post-eruption recovery of ecosystems affected by the Toba event provides insights into the resilience and vulnerability of biological communities to extreme environmental perturbations. Pollen records from sediment cores spanning the eruption horizon document the collapse and subsequent recovery of forest ecosystems. Vegetation changes that occurred over centuries to millennia following the initial volcanic impact. Some plant communities show evidence for complete local extinction, followed by recolonization from distant refugia, while others demonstrate remarkable persistence through the volcanic crisis. The mineralogy of Toba ash reveals information about the depth and thermal conditions within the magma chamber prior to eruption. Quartz phenocrysts preserve evidence for multiple episodes of magma reheating and cooling, while feldspar compositions indicate the pressure and temperature conditions that existed during crystal growth. Even the vesicle structure of volcanic glass provides information about the gas content and explosive violence that characterize the eruption process. Modern volcanic monitoring systems provide insights into the precursory activity that may have preceded the Toba eruption, ground deformation and seismic activity that characterizes magma chamber pressurization prior to explosive events. Contemporary examples of large silicic volcanic systems, including Yellowstone and Long Valley, operate under conditions that may be analogous to those that existed prior to the Toba eruption. The atmospheric chemistry changes caused by the Toba eruption affected global precipitation patterns and atmospheric circulation systems in ways that influenced regional climate conditions for years following the event. Ice core records from both hemispheres preserve evidence for the timing and magnitude of these climate effects. Volcanic signals that appear synchronously in glacial archives worldwide. The wind patterns that distributed Toba ash across the globe operated according to atmospheric circulation systems that were similar to, yet subtly different from, contemporary patterns. The position of the jet stream, the intensity of monsoon circulation, and the strength of trade wind systems all influence the final distribution of volcanic debris, creating deposition patterns that provide insights into late Pleistocene atmospheric dynamics. The economic minerals that crystallized within the Toba magma chamber prior to eruption include tin, tungsten, and other strategically important elements that concentrate in highly evolved silicic melts. The mining districts that exploit these volcanic-related mineral deposits represent indirect benefits derived from catastrophic geological processes. Economic resources created through the same magmatic evolution that led to explosive volcanism. Contemporary tephra studies continue to refine understanding of explosive volcanic processes and their global environmental effects. Modern analytical techniques allow identification of volcanic ash layers at concentrations approaching parts per million, enabling correlation of volcanic events across intercontinental distances. These studies provide insights into the frequency and magnitude of explosive eruptions that may occur in the future. Information crucial for assessing volcanic hazards in densely populated regions. The ancient rivers move across landscapes with the fluid persistence of liquid-seeking equilibrium, their channels wandering through alluvial plains in sinuous patterns that follow the mathematics of flow dynamics and the patient geography of sediment transport. These Paleogene waterways carve their stories into stone through processes that operate on timescales spanning millions of years, each meander loop representing thousands of years of lateral migration, each oxbow lake marking a moment when flowing water abandoned its previous course and carved a new path across the floodplain. The river that will eventually become fossilized in the Willwood Formation of Wyoming begins its journey in highland areas where laramide mountain building has elevated ancient sedimentary rocks into ranges that intercept moisture from atmospheric circulation patterns unlike any that exist today. The early Eocene climate supports global temperatures several degrees warmer than contemporary conditions, creating atmospheric water content that drives precipitation patterns across North America with tropical intensity even at latitudes that currently experience temperate conditions. The channel itself possesses dimensions that dwarf most modern river systems, its width approaching that of the contemporary Mississippi River, yet flowing through landscapes that support vegetation communities unlike any that have existed since the Paleogene period. Vast forests of dawn redwoods, ancestors of trees that will eventually retreat to refugial populations in Eastern Asia, line the riverbanks with trunk diameters exceeding 5 meters and canopy heights that create cathedral-like spaces beneath their branches. The sediment load carried by this ancient river contains material eroded from mountain ranges whose peaks have been ground to powder by 50 million years of subsequent weathering and erosion. Sand grains carry trace element signatures that indicate their derivation from specific rock formations, isotopic compositions that allow geologists to reconstruct the elevation and erosional history of source areas that no longer exist in recognizable form. Clay minerals within the river sediments preserve evidence for soil formation processes that operated under greenhouse climatic conditions. The meandering pattern that characterizes this river system follows physical principles that remain unchanged since water first began flowing across continental surfaces. The channel migrates laterally through processes of bank erosion and point bar deposition, cutting into the outside of meander bends while simultaneously depositing sediment on the inside curves. This lateral migration occurs at rates measured in meters per year, yet the cumulative effect over geological time creates channel belt widths that exceed the instantaneous channel width by factors of 10 or more. The point bar deposits that accumulate on the inside of meander bends preserve detailed records of river behavior and discharge patterns. Individual beds within these deposits represent flood events of varying magnitude, their grain size and thickness indicating the velocity and sediment concentration of floodwaters that have not flowed for 50 million years. The cross-bedding within point bar sands records current directions with compass precision, documenting flow patterns during specific flood events that occurred during single seasons of Paleogene time. The oxbow lakes that form when the river abandons meander, loops through neck cutoff events, become repositories for fine-grained sediments and organic matter that preserve extraordinary records of terrestrial ecosystem conditions. These abandoned channels fill gradually with clay and silt deposited during seasonal floods, creating anaerobic environments where plant and animal remains achieve exceptional preservation. Fossil leaves retain cellular detail that allows identification to species level, while insect fossils preserve wing venation patterns and body segmentation with microscopic fidelity. Only took 10,000 years for individual meander loops to complete full cycles of lateral migration and abandonment. Only required the persistent lateral erosion of riverbanks to create channel belt deposits hundreds of meters wide. Only demanded the gradual filling of oxbow lakes with fine sediments to preserve detailed records of riparian ecosystem conditions across millions of years. The vertebrate fossils found within these river deposits document one of the most important intervals in mammalian evolutionary history. The adaptive radiation that followed the end Cretaceous mass extinction and led to the establishment of modern mammalian orders. Complete skeletons of early horses, primates, and carnivores preserve anatomical details that illuminate evolutionary transitions from primitive to more derived morphological conditions. The three-dimensional preservation of these fossils results from rapid burial in river sediments during flood events that entombed carcasses before decomposition could destroy bone and soft tissue. The Paleosol horizons that develop on river floodplains between major flood events preserve information about ancient soil chemistry, precipitation patterns, and vegetation structure during the early Eocene greenhouse period. These buried soils show evidence for intense chemical weathering under warm, humid conditions, mineral alteration patterns that indicate mean annual temperatures exceeding those of modern tropical regions. The root traces preserved within Paleosol profiles document plant community structure and rhizosphere chemistry that supported forest ecosystems of extraordinary productivity. The mystery embedded in these ancient river deposits concerns the hydrological conditions that maintained such large channel dimensions and high sediment transport capacity. Modern rivers of comparable size operate under different climatic and topographic boundary conditions, making direct comparison with ancient systems problematic. Perhaps the greenhouse climatic conditions of the early Eocene supported more intense precipitation and runoff than contemporary river systems experience. Perhaps the tectonic activity associated with laramide mountain building provided greater relief and sediment supply than modern passive margin settings. The trace fossil assemblages within river channel deposits provide evidence for the terrestrial organisms that inhabited riparian environments during the Paleogene period. Mammal trackways preserved on point bar surfaces document feeding behaviors, social interactions, and seasonal migration patterns of early Cenozoic faunas. Insect burrows and root traces create complex networks within river sediments, evidence for biological activity that extended meters below the active river channel. In exposures along the Bighorn River, these ancient channel deposits appear as laterally continuous sandstone bodies that can be traced for tens of kilometers along strike, their internal architecture revealing the three-dimensional geometry of meandering river systems. The thickness and lateral extent of individual channel bodies provide information about channel dimensions and migration patterns, while the vertical stacking of multiple channel stories documents the long-term evolution of river systems over millions of years. The plant fossils preserved within Oxbow Lake deposits include some of the most complete and diverse Paleogene flora known from North America. Fossil leaves represent more than 300 species of flowering plants, conifers, and ferns, diversity levels that exceed those of modern temperate forests by substantial margins. The morphological analysis of leaf architecture provides information about ancient precipitation patterns, atmospheric carbon dioxide concentrations, and temperature regimes that characterized early Eocene climatic conditions. The geochemistry of ancient river sediments preserves information about weathering processes and atmospheric chemistry during their deposition. Clay mineral assemblages indicate the intensity of chemical weathering in source areas, while trace element concentrations reflect the composition of parent rocks and the efficiency of sediment transport processes. Even the carbon isotope ratios of organic matter within river deposits provide information about photosynthetic pathways and atmospheric carbon dioxide concentrations. Modern meandering rivers provide analogs for understanding the processes that created these ancient channel deposits. Though contemporary river systems operate under different climatic and base-level conditions, comparative studies of modern and ancient meandering systems illuminate the relationships between climate, tectonics, and river behavior across geological timescales. The preservation of river channel deposits requires specific geological conditions that allow laterally migrating channels to be buried and protected from subsequent erosion. Subsidence rates must balance sediment supply rates to create accommodation space for channel preservation, while base-level changes must remain within limits that prevent extensive erosion of previously deposited sediments. The wind patterns across contemporary exposures of these ancient river deposits carry particles that contain the molecular signatures of Paleogene watershed processes, organic compounds and mineral fragments that preserve evidence for soil formation, plant growth, and erosional processes that operated under greenhouse climatic conditions. Each grain represents material that was transported by river systems that drained mountain ranges and crossed floodplains that no longer exist in recognizable form. The architectural elements preserved within these ancient river deposits continue to serve as models for understanding subsurface reservoir geometry in petroleum and groundwater systems. The three-dimensional connectivity of channel sands and the distribution of impermeable floodplain muds control fluid flow patterns in ways that reflect the original depositional architecture of meandering river systems. Contemporary sedimentological research continues to refine understanding of river meandering processes and their preservation potential in the geological record. Advanced imaging techniques and computational modeling studies provide insights into the physical mechanisms that control channel migration and the conditions necessary for exceptional fossil preservation in fluvial environments. The ancient coastlines pulse with wave energy driven by storm systems that gather strength across ocean basins larger than any that exist today. Their tempestuous winds whipping surface waters into swells that travel thousands of kilometers before breaking against shores where no human footprint will appear for hundreds of millions of years. These Ordovician storm beaches accumulate sediments under wave conditions that exceed those of modern hurricane systems, creating deposits that preserve evidence for atmospheric circulation patterns and ocean dynamics operating under continental configurations that challenge contemporary understanding of global climate systems. The storm waves that approach these ancient shores carry energy accumulated across fetch distances that span entire ocean basins. Surface waters set in motion by wind systems driven by pressure gradients between high and low atmospheric circulation centers. The waves themselves reach heights exceeding 20 meters, with wavelengths measured in hundreds of meters and periods that cause the entire water column to oscillate with each passing crest. When these massive swells encounter the shallow water of continental shelves, they begin the complex process of energy dissipation that will create the beach deposits preserved in the geological record. The beach face that receives these waves consists of carbonate sediments unlike any that accumulate in modern marine environments, composed primarily of skeletal fragments from organisms that have no contemporary equivalents. Crinoid stems, broken from sea lilies that covered vast areas of Ordovician seafloor like underwater meadows, provide coarse sand-sized particles with distinctive cylindrical shapes and crystalline internal structures. Brachiopod shells, their ribbed surfaces polished smooth by wave action, contribute calcium carbonate grains that reflect biological productivity levels far exceeding those of modern marine ecosystems. The wave processes that sort and transport these skeletal fragments operate according to physical principles that remain unchanged since the first oceans formed. Yet they create deposits under boundary conditions that have not existed since the Paleozoic era. The oscillatory motion of storm waves alternately moves sediment onshore and offshore, creating characteristic sedimentary structures that document wave energy, water depth, and the frequency of storm events. Crossbedding within beach deposits records the direction of sediment transport during individual storm episodes, while the thickness of storm beds indicates the magnitude and duration of wave energy. The tempestites that result from these ancient storms appear as distinctive layers within otherwise normal marine sequences, beds of coarse-grained carbonate debris interbedded with fine-grained sediments that accumulated during fair weather conditions. These storm deposits often contain a mixture of shallow water and deeper water organisms, evidence for the ability of powerful waves to transport marine life across environmental gradients that normally serve as effective ecological barriers. The hummocky cross-stratification that characterizes many of these storm deposits forms through wave processes that operate in water depths between normal wave base and storm wave base, creating sedimentary structures that document the interaction between oscillatory and unidirectional flow components. The wavelength and amplitude of these hummocky structures provide information about storm wave characteristics, while their orientation indicates the dominant direction of wave approach during major storm events. Only took hours for individual storms to generate the wave energy necessary to transport coarse carbonate debris across kilometers of shallow shelf. Only required the episodic occurrence of major storm systems to create beds that dominate the stratigraphic record of ancient shallow marine environments. Only demanded the preservation of storm deposits beneath fair weather sediments to create detailed archives of ancient atmospheric circulation and ocean wave dynamics. The fossil assemblages within these storm beach deposits preserve communities of marine organisms that were subjected to high-energy wave conditions unlike any that characterize modern coastal environments. The shells and skeletal fragments show evidence for extensive abrasion and transport, their surfaces polished and rounded by tumbling in the surf zone during storm events. Yet some specimens preserve delicate structures that indicate rapid burial following transport, protection from continued wave action by burial beneath subsequent sediment layers. The size sorting that occurs within storm beach deposits follows hydraulic principles that allow reconstruction of wave energy and flow velocity during ancient storm events. The largest skeletal fragments accumulate in the highest energy portions of the beach profile, while finer-grained material settles in protected areas behind barrier structures or in deeper water beyond the reach of storm waves. The vertical grading within individual storm beds documents the waning energy conditions as storm systems moved offshore and wave heights gradually decreased. The mystery embedded in these ancient storm deposits concerns the atmospheric and oceanic circulation patterns that generated such powerful wave systems across the Ordovician ocean basins. The continental configurations of the Ordovician period created ocean geometries unlike any that exist today, potentially allowing storm systems to develop greater intensity over longer fetch distances than contemporary hurricanes can achieve. Perhaps the greenhouse climatic conditions of the Ordovician period supported more vigorous atmospheric circulation than modern climate systems experience. The trace fossil assemblages within storm beach deposits provide evidence for the behavioral responses of marine organisms to high-energy wave conditions. Escape burrows document the ability of some organisms to respond to rapid burial by storm sediments, while the absence of normal dwelling traces indicates that regular wave action prevented the establishment of stable infaunal communities. The distribution of trace fossils across storm bed sequences reveals the colonization patterns that followed major storm events. In exposures across the Cincinnati Arch region, these Ordovician storm deposits create distinctive weathering patterns that allow identification of individual storm beds across hundreds of kilometers of outcrop area. The lateral continuity of these beds indicates that single storm systems affected vast areas of the continental shelf, creating deposits that preserve evidence for storm intensity and track across entire sedimentary basins. The geochemistry of storm beach sediments preserves information about seawater composition and atmospheric chemistry during the Ordovician period. Trace element concentrations within skeletal carbonates indicate ocean temperature and salinity conditions, while carbon and oxygen isotope ratios provide information about marine productivity and atmospheric carbon dioxide levels. Even the preservation state of carbonate minerals reflects the diagenetic history and burial environment of storm deposits. The sequence stratigraphic context of these storm deposits reveals their relationship to sea level changes and long-term patterns of sediment accumulation. Storm beds often concentrate at specific stratigraphic levels that correspond to periods of maximum sediment supply or optimal water depth conditions for storm wave interaction with the seafloor. The vertical stacking patterns of storm deposits provide information about the frequency and intensity of storm systems over millions of years. Modern storm beach systems provide analogs for understanding the formation processes that created these ancient deposits. Though contemporary coastal environments operate under different oceanic and atmospheric boundary conditions, hurricane research and coastal sedimentology studies illuminate the physical mechanisms of storm wave generation and sediment transport, processes that operated similarly during the Ordovician period despite different continental and climatic configurations. The preservation potential of storm beach deposits depends on rapid burial beneath subsequent sediments and protection from erosion during fair weather periods. The high porosity and permeability of carbonate beach deposits makes them susceptible to dissolution and diagenetic alteration, processes that can destroy the original sedimentary structures and fossil content unless burial occurs rapidly enough to exclude meteoric waters. The wind patterns that generated these ancient storm systems operated according to atmospheric circulation principles that remain unchanged. Yet they developed under continental arrangements and climatic conditions that have no modern equivalents. The Coriolis effect, pressure gradient forces, and thermal circulation patterns combined to create storm systems that achieved intensities and maintained persistence across ocean basins of different size and configuration than contemporary systems. Contemporary coastal research continues to refine understanding of storm wave processes and their geological preservation potential. Studies of modern hurricane deposits and tsunami sediments provide insights into the formation mechanisms and diagnostic criteria for identifying ancient storm deposits, information crucial for interpreting the paleo-environmental significance of tempestite sequences. The carbonate mineralogy of these ancient storm deposits reflects seawater chemistry conditions that differed significantly from modern ocean composition. The predominance of low magnesium calcite in Ordovician skeletal carbonates indicates ocean chemistry that favored different mineral precipitation than contemporary marine systems. Changes related to atmospheric carbon dioxide levels and global climate conditions. The bioturbation patterns within storm beach sequences document the recovery of benthic communities following major storm disturbance events. The vertical succession of trace fossil assemblages records ecological succession as marine organisms recolonized storm-disturbed seafloor areas, community development patterns that provide insights into the resilience and recovery potential of ancient marine ecosystems. Modern sedimentological and paleontological research continues to extract new information from these ancient storm deposits as analytical techniques become increasingly sophisticated. High-resolution imaging and geochemical analysis provide detailed information about storm wave characteristics, while computational modeling studies test hypotheses about ancient atmospheric and oceanic circulation patterns under different continental configurations. The ancient forests of the Cretaceous period breathe through resin that flows like golden blood from wounds in bark structures that have no contemporary equivalents. Their aromatic secretions carrying the chemical signatures of atmospheric composition and botanical physiology operating under greenhouse conditions that have not existed since an asteroid redefined the boundaries between geological ages. These coniferous trees, ancestors of modern pine and fir species, yet possessing anatomical features that disappeared with the dinosaurs, produce resin in quantities that exceed anything documented in modern forest ecosystems. Sticky, amber-colored flows that trap insects, spores, plant fragments, and actual samples of ancient atmosphere. The resin production occurs in response to injury boring insects that tunnel through bark, fungal infections that penetrate sapwood, mechanical damage from browsing dinosaurs whose feeding behaviors create wounds that stimulate defensive chemical responses. The trees synthesize complex hydrocarbon compounds that polymerize upon exposure to air, creating protective barriers against infection while simultaneously preserving microscopic samples of Cretaceous life with fidelity that approaches that of laboratory preparation techniques. The chemical composition of tree resin reflects the physiological responses of plants to atmospheric conditions that differ dramatically from contemporary air chemistry. Carbon dioxide concentrations during the mid-Cretaceous period exceed modern levels by factors of 4 to 6, creating conditions that saturate the photosynthetic pathways of most plant species and drive productivity to levels that approach the theoretical limits of terrestrial ecosystem function. Oxygen concentrations remain elevated compared to modern atmosphere, supporting metabolic processes in both plants and animals that operate at rates enhanced by the availability of this crucial respiratory gas. The insects that become trapped in flowing resin represent fauna that have no exact modern equivalents, yet their preservation quality allows identification of anatomical structures down to individual muscle fibers and cellular organelles. Primitive ants with morphological features that bridge the evolutionary gap between wasps and modern social insects appear frozen in moments of ordinary activity, grooming antennae, manipulating food particles, engaging in behaviors that illuminate the social organization of early eusocial communities. Flying insects preserve wing venation patterns, compound eye structures, and even the contents of digestive systems that contain pollen from plants that became extinct 65 million years ago. The atmospheric samples trapped within amber represent the most direct evidence available for ancient air composition. Actual bubbles of Cretaceous atmosphere preserved within resin matrices that have remained chemically stable for hundreds of millions of years. These gas inclusions contain measurable concentrations of oxygen, carbon dioxide, nitrogen, and trace gases that provide empirical data for testing models of ancient atmospheric evolution. The isotopic composition of trapped gases reflects atmospheric chemistry operating under different volcanic outgassing rates, continental configuration, and biological productivity than any documented in subsequent Earth history. The plant fragments preserved within amber include microscopic pollen, spores, wood fragments, and even complete leaves from vegetation communities that dominated Cretaceous landscapes. Angiosperm pollen reveals the early diversification of flowering plants during their initial adaptive radiation, morphological innovations in reproductive structures that enabled the evolutionary success that would eventually make flowering plants the dominant terrestrial vegetation worldwide. Conifer needles and wood fragments preserve cellular structures that indicate adaptation to atmospheric carbon dioxide concentrations far exceeding those that contemporary plants experience. Only took minutes for flowing resin to encapsulate small organisms and atmospheric samples before polymerization excluded further chemical exchange with the environment. Only required the chance encounter between resin flow and living organisms to create preservation conditions that exceed those achieved by any other fossilization process. Only demanded the burial of resin deposits beneath sediments that excluded oxygen and prevented degradation for hundreds of millions of years. The microorganisms preserved within amber represent some of the oldest direct evidence for bacterial and fungal communities that inhabited Cretaceous forest ecosystems. Individual bacterial cells preserve morphological details that allow identification of specific lineages, while fungal spores and hyphae document the diversity of decomposer organisms that recycled organic matter under atmospheric conditions unlike any that exist today. Some specimens preserve evidence for symbiotic relationships between plants and microorganisms, ancient versions of mycorrhizal associations that enhanced nutrient uptake in high carbon dioxide environments. The behavioral preservation within amber extends beyond simple anatomical details to capture moments of ecological interaction frozen in geological time. Parasitic mites attached to host insects document ancient host-parasite relationships, while pollen grains adhering to insect bodies provide evidence for pollination networks that connected flowering plants with their animal vectors. Some specimens preserve evidence for predation events, social interactions, and reproductive behaviors that illuminate the ecological complexity of Cretaceous terrestrial ecosystems. The mystery embedded in amber deposits concerns the extraordinary preservation quality that maintains cellular structures and molecular information across hundreds of millions of years. Modern resin polymerization processes operate similarly to ancient systems. Yet contemporary amber formation occurs under different atmospheric chemistry and burial conditions than those that characterized Cretaceous environments. Perhaps the specific chemical composition of ancient tree resins provided superior preservation properties compared to modern equivalents. The geographic distribution of amber deposits reveals information about ancient forest composition and the ecological conditions that favored resin production. Major amber deposits occur in regions that experienced tropical or subtropical climates during the Cretaceous period, areas where coniferous forests achieved maximum productivity under greenhouse atmospheric conditions. The temporal distribution of amber-producing intervals corresponds to periods of elevated global temperature and atmospheric carbon dioxide concentrations. In the amber mines of Myanmar, specimens preserve Cretaceous forest ecosystems with unprecedented completeness. Entire ecological communities trapped within individual pieces of fossilized resin, feathered dinosaur tails, complete with bone, muscle, and integumentary structures, provide direct evidence for the morphological transitions that led from non-avian dinosaurs to modern birds. These specimens preserve biological details that are never found in conventional fossil deposits, soft tissue structures that decay within days in normal depositional environments. The isotopic composition of amber preserves information about ancient plant physiology and atmospheric chemistry during resin formation. Carbon isotope ratios indicate the photosynthetic pathways utilized by resin-producing trees, while hydrogen isotope signatures reflect precipitation patterns and relative humidity conditions during tree growth. Even the sulfur isotope ratios preserve information about atmospheric chemistry and volcanic outgassing rates during the Cretaceous period. The spectroscopic analysis of amber reveals molecular information about ancient biochemical processes and the chemical evolution of life on Earth. Infrared spectroscopy identifies specific organic compounds preserved within amber matrices, while mass spectrometry detects trace amounts of ancient biomolecules that retain information about protein structures and metabolic pathways. Some specimens contain amino acids and other organic compounds that preserve molecular signatures of Cretaceous life. Modern resin production and amber formation provide insights into the processes that created ancient amber deposits, though contemporary forests operate under atmospheric conditions significantly different from those that characterize the Cretaceous period. Studies of modern conifer resin chemistry and polymerization processes illuminate the mechanisms that led to exceptional preservation quality in ancient forest environments. The paleontological significance of amber extends beyond its exceptional preservation quality to its documentation of evolutionary transitions and ancient biodiversity patterns. The temporal distribution of amber deposits provides snapshots of ecosystem composition during critical intervals in Earth's biological history, including the early diversification of flowering plants, the evolution of social insects, and the transition from dinosaur-dominated to mammal-dominated terrestrial communities. Contemporary analytical techniques continue to extract new information from amber specimens as technology advances enable increasingly detailed investigation of preserved biological materials. High-resolution imaging techniques reveal cellular and subcellular structures, while geochemical analyses provide information about ancient atmospheric composition and climate conditions. Even ancient DNA extraction attempts, though largely unsuccessful, continue to push the boundaries of molecular paleontology. The taphonomic processes that led to amber formation represent unique combinations of biological, chemical, and geological factors that occur rarely in contemporary environments. The specific conditions necessary for exceptional preservation in amber-abundant resin production, rapid burial, anoxic diagenetic environments create natural laboratories for understanding fossilization processes and the factors that determine preservation quality across geological time. The wind patterns across contemporary amber-bearing outcrops carry particles that contain the molecular signatures of ancient forest chemistry, organic compounds weathered from amber deposits that preserve chemical information about Cretaceous atmospheric composition. Each grain represents accumulated plant secondary metabolites and atmospheric samples that document greenhouse climate conditions and forest ecosystem function under environmental parameters that have no modern analogues. The caves that honeycomb limestone formations across continents serve as Earth's most patient meteorological stations, their mineral formations growing grain by grain through chemical processes that record atmospheric conditions with the precision of laboratory instruments and the temporal resolution of seasonal cycles spanning hundreds of thousands of years. Within these underground chambers, speleothems develop through the slow precipitation of calcium carbonate from groundwater that has percolated through soil horizons and bedrock formations, carrying dissolved minerals and chemical signatures that reflect surface climate conditions, vegetation patterns, and atmospheric composition at the time of their formation. The stalactites that hang from cave ceilings like stone icicles grow through processes that operate on timescales spanning millennia, each annual growth layer representing a single year of precipitation chemistry filtered through soil systems and limestone bedrock. Water droplets that form at stalactite tips contain dissolved calcium carbonate in chemical equilibrium with atmospheric carbon dioxide. Cave air composition and the temperature conditions that exist at the interface between liquid water and cave atmosphere. When these droplets evaporate or lose carbon dioxide to cave air, calcium carbonate precipitates in crystalline layers that preserve information about surface climate conditions. The stalagmites that rise from cave floors beneath dripping stalactites accumulate sediment records that extend far beyond the temporal range of ice cores, tree rings, or any other paleoclimate archive. Individual growth layers, visible in polished cross-sections as alternating bands of light and dark calcite, represent annual cycles of precipitation, temperature, and vegetation productivity that affected groundwater chemistry during their formation. The thickness of annual layers indicates the amount of precipitation that occurred during individual years, while the chemical composition reflects temperature, atmospheric composition, and soil development processes. The trace element chemistry preserved within speleothem calcite provides detailed information about ancient environmental conditions operating above the cave systems. Magnesium concentrations correlate with temperature conditions during calcite precipitation, while strontium levels indicate the degree of water-rock interaction during groundwater flow through limestone formations. Rare earth element patterns reflect soil chemistry and the efficiency of chemical weathering processes that operated under different climate regimes. The isotopic composition of speleothem calcite preserves information about atmospheric circulation patterns, precipitation sources, and temperature conditions with temporal resolution that often exceeds that of instrumental climate records. Oxygen isotope ratios reflect the temperature and isotopic composition of precipitation that recharged groundwater systems, while carbon isotope signatures indicate vegetation type and soil respiration processes above cave systems. The seasonal resolution preserved in rapidly growing speleothems allows reconstruction of ancient weather patterns and climate variability. The uranium-thorium dating of speleothems provides chronological frameworks that extend back several 100,000 years, temporal coverage that spans multiple glacial-interglacial cycles and major climate transitions. The decay of uranium isotopes incorporated into calcite during precipitation creates daughter thorium isotopes that accumulate at rates determined by known radioactive decay constants. allowing precise age determination for speleothem growth layers with uncertainties measured in decades rather than millennia. Only took centuries for individual speleothems to grow sufficiently to preserve climate information spanning human historical periods. Only required the patient accumulation of annual growth layers to create climate archives extending back through multiple ice ages. Only demanded the chemical stability of calcite minerals to preserve climate information for hundreds of thousands of years without significant alteration. The growth rate variations preserved in speleothem sequences reflect changes in precipitation amount, seasonality, and the efficiency of soil zone carbon dioxide production that drives limestone dissolution. Periods of rapid speleothem growth correspond to intervals of increased precipitation and enhanced soil biological activity, while slow growth or cessation indicates arid conditions or frozen ground that prevented effective groundwater recharge. Some speleothems show evidence for complete growth cessation during glacial periods, indicating climate conditions too cold or dry to maintain active cave hydrology. The fluid inclusion analysis of speleothem calcite provides direct samples of ancient groundwater trapped during mineral precipitation, chemical compositions that reflect atmospheric and soil chemistry conditions during speleothem formation. These microscopic water samples contain dissolved ions, trace gases, and organic compounds that preserve information about ancient atmospheric composition, soil development, and vegetation communities that existed above cave systems during different climate periods. The mystery embedded in speleothem climate records concerns the mechanisms that translate surface climate conditions into underground chemical signals with such remarkable fidelity and temporal precision. The pathways through which atmospheric circulation patterns, temperature changes, and precipitation variations influence groundwater chemistry involve complex interactions between atmospheric processes, soil development, and limestone hydrology that operate over timescales ranging from seasons to millennia. The paleomagnetic properties of speleothems provide additional chronological information and indicators of ancient climate conditions. Magnetic minerals incorporated into calcite during precipitation preserve records of geomagnetic field intensity and direction, while magnetic susceptibility variations reflect changes in the supply of wind-blown dust and soil erosion that occurred above cave systems during different climate periods. In cave systems across Europe, Asia, and the Americas, speleothem records preserve detailed documentation of climate transitions that accompanied major episodes in human cultural development. The medieval warm period, Little Ice Age, and other historical climate anomalies appear with annual resolution in speleothem growth records, providing ground truth data for testing climate models and understanding the relationships between climate variability and human society development. The organic matter preserved within speleothems includes pollen, spores, and organic compounds that document vegetation changes and ecosystem development above cave systems. These biological markers provide information about forest composition, agricultural development, and land use changes that accompanied human settlement and technological advancement. Some speleothems preserve evidence for specific vegetation types and their responses to climate transitions over thousands of years. The cave environments that support speleothem formation maintain remarkably stable temperature and humidity conditions that facilitate mineral precipitation and preserve climate information with minimal post-depositional alteration. Cave air circulation patterns, groundwater flow rates, and limestone chemistry create microenvironments that operate as natural laboratories for understanding mineral precipitation processes and their sensitivity to surface climate conditions. Modern speleothem formation provides opportunities for calibrating ancient climate reconstructions against instrumental meteorological records. validation studies that illuminate the relationships between surface climate conditions and underground mineral precipitation. Contemporary monitoring of cave hydrology, groundwater chemistry, and speleothem growth rates provides insights into the mechanisms that control climate signal transfer from surface to subsurface environments. The preservation potential of speleothems depends on cave environmental conditions that exclude meteoric water infiltration, mechanical erosion, and chemical alteration processes that could destroy original climate signals. The best preserved speleothem climate records occur in caves with stable hydrology, minimal human disturbance, and limestone host rocks that provide chemical buffering against diagenetic alteration. The analytical techniques applied to speleothem climate reconstruction continue to improve as mass spectrometry and imaging technologies advance to provide increasingly detailed chemical and isotopic information. Microsampling techniques enable analysis of individual annual growth layers, while laser ablation methods provide spatial resolution that approaches the scale of daily growth increments in rapidly precipitating speleothems. The global distribution of speleothem climate records provides opportunities for reconstructing ancient atmospheric circulation patterns and testing climate models against empirical data, spanning hundreds of thousands of years. Regional networks of speleothem records document the spatial patterns of climate change and the synchronicity of climate transitions across different geographical regions and climate zones. Contemporary cave monitoring studies continue to refine understanding of the processes that control speleothem formation and climate signal preservation. Automated data logging systems track cave air temperature, humidity, carbon dioxide concentrations, and drip water chemistry at temporal resolutions that provide insights into seasonal and annual variations in cave environments. The wind patterns that affect cave air circulation and speleothem formation reflect regional atmospheric circulation systems and topographic influences that control airflow through underground passages. Barometric pressure variations drive air exchange between cave and surface environments, while seasonal temperature changes create thermal circulation patterns that influence cave air chemistry and mineral precipitation rates. The hydrological processes that control groundwater flow through limestone formations reflect precipitation patterns, soil development, and bedrock permeability characteristics that determine the residence time and chemical evolution of water that eventually reaches cave environments. Understanding these hydrological pathways provides insights into the time lags between surface climate changes and their expression in speleothem growth records. The contemporary sediments that accumulate beneath modern skies continue the ancient tradition of atmospheric documentation, their mineral grains settling through water columns and across terrestrial surfaces with the same patient persistence that has characterized geological record-keeping since the first oceans formed on a cooling planet. Today's storms leave their signatures in lakebed clays and deep-sea oozes. Tomorrow's weather patterns will find expression in sedimentary structures that future geologists may study with technologies not yet imagined. Each grain of sand and particle of dust carrying forward the endless conversation between atmosphere and stone. The processes that create these modern archives operate according to physical and chemical principles unchanged since the Archean. Yet they document atmospheric conditions that represent a unique moment in Earth's 4.6 billion-year history. Carbon dioxide concentrations approach levels not experienced since the Pliocene, while the chemical composition of precipitation reflects industrial activities that have altered atmospheric chemistry on a global scale. The sediments forming today will preserve evidence for this anthropogenic influence with the same fidelity that characterized the documentation of natural climate variations throughout geological time. In lake basins across the continents, Annual sediment layers accumulate like pages in books written by seasonal cycles of erosion, biological productivity, and atmospheric deposition. Varved lake sediments preserve information about precipitation patterns, temperature variations, and storm frequency with annual resolution, their alternating light and dark bands reflecting the eternal rhythm of seasons and the chemical responses of watersheds to atmospheric conditions. These contemporary deposits continue traditions of climate documentation that extend back through ice ages, greenhouse periods, and mass extinction events. The urban atmospheric chemistry recorded in modern sediments includes trace metals, synthetic organic compounds, and isotopic signatures that have no equivalents in pre-industrial geological formations. Lead concentrations track the history of automobile emissions, while plastic microparticles document the development of polymer chemistry and global waste distribution. These anthropogenic signals will serve as stratigraphic markers for future investigators, time horizons as distinctive as volcanic ash layers or impact debris in older geological formations. The marine sediments that accumulate on contemporary ocean floors continue the slow construction of stratigraphic sequences that began with the first formation of seafloor basalts billions of years ago. 4M, iniferal shells preserve isotopic records of ocean temperature and chemistry, while wind-blown dust documents atmospheric circulation patterns and continental aridity. Each annual layer of deep-sea sediment adds new information to archives that already span millions of years of Earth's climate history. The ice sheets of Greenland and Antarctica accumulate snow that will eventually become the deep ice cores studied by future paleoclimatologists. Atmospheric samples trapped in crystalline matrices that preserve air composition with greater temporal resolution than any other climate archive. The snow falling today contains atmospheric chemistry altered by human activities, volcanic eruptions, and natural climate variations that operate on timescales from seasons to centuries. Only requires decades for modern sediment accumulation to preserve detailed records of contemporary atmospheric conditions. Only demands the continued operation of erosion, transport, and deposition processes to extend geological archives into future time. Only needs the patient accumulation of mineral grains to document the atmospheric conditions that characterize the current moment in Earth's long climatological evolution. The pollen and spores settling into modern lake sediments document contemporary vegetation patterns and their responses to changing climate conditions, agricultural development, and urban expansion. These biological particles will preserve information about current ecosystem composition for future paleoecologists, adding new chapters to pollen records that already extend back through multiple glacial-interglacial cycles. The disappearance of some species and the introduction of others creates biological signals that mark the transition from natural to anthropogenically influenced environments. The chemical weathering processes that supply dissolved ions to modern river systems operate under atmospheric carbon dioxide concentrations that enhance carbonic acid formation and accelerate rock dissolution rates compared to pre-industrial conditions. The increased acidity of precipitation reflects atmospheric chemistry alterations that will leave permanent signatures in sedimentary formations, chemical fingerprints of industrial activity preserved in limestone, shale, and sandstone formations. The mystery that will challenge future geologists concerns the mechanisms through which rapid anthropogenic changes interact with natural climate variability and long-term geological processes. The timescales of human influence represent geological moments compared to the million-year cycles that characterize most natural climate transitions. Yet the magnitude of atmospheric chemistry changes approaches those documented during major geological events like volcanic supereruptions or asteroid impacts. The coral reefs that grow in modern tropical seas incorporate atmospheric carbon dioxide into their calcium carbonate skeletons, creating archives that document ocean acidification and temperature changes with monthly resolution. These biological formations preserve isotopic records of industrial carbon emissions and their effects on marine chemistry, chemical signals that will persist in limestone formations long after the reefs themselves have been buried beneath younger sediments. In polar regions, the ice sheets that accumulate contemporary snowfall preserve atmospheric samples that document the exact composition of air during specific years, seasons, and even individual storm events. Future ice core researchers will be able to trace atmospheric carbon dioxide concentrations, trace gas compositions, and volcanic ash deposition with unprecedented temporal precision, creating climate records that bridge the gap between instrumental measurements and geological archives. The wind patterns that distribute modern atmospheric dust operate according to circulation systems altered by changing temperature gradients, modified land use patterns, and urban heat island effects that influence regional climate conditions. Contemporary aeolian deposits preserve evidence for these anthropogenically influenced atmospheric circulation patterns, sedimentary structures that document the interaction between natural and human-modified environmental systems. The volcanic ash that falls from contemporary eruptions adds new tephrochronological markers to sedimentary sequences worldwide, time parallel horizons that will allow future stratigraphers to correlate geological formations with precision measured in days rather than thousands of years. These modern ash layers will serve as reference points for understanding the rates and patterns of sediment accumulation in different depositional environments. The trace fossil assemblages forming in modern sedimentary environments include evidence for organisms responding to changed atmospheric and oceanic chemistry, behavioral adaptations to environmental conditions that have no precedence in Earth's previous history. The bioturbation patterns created by contemporary marine organisms reflect ecosystem responses to ocean acidification, temperature changes, and altered food web structures that accompany anthropogenic environmental modifications. Modern sedimentological research continues to refine understanding of the processes that control climate signal preservation in different depositional environments. Real-time monitoring of sediment accumulation, water chemistry, and atmospheric deposition provides insights into the mechanisms that determine which climate information becomes permanently archived in geological formations and which signals are lost through post-depositional alteration. The isotopic composition of modern precipitation reflects atmospheric circulation patterns, evaporation sources, and temperature conditions that will be preserved in speleothems, lake sediments, and groundwater systems for hundreds of thousands of years. These chemical signatures document contemporary climate conditions with the same fidelity that characterizes ancient climate reconstructions, adding new data to geological archives that span Earth's entire climatic evolution. The technological advances that characterize contemporary analytical capabilities provide unprecedented opportunities for documenting modern environmental conditions and understanding the processes that control geological preservation. Satellite remote sensing, automated monitoring systems, and high-resolution analytical techniques create observational datasets that future investigators will use to understand the relationships between atmospheric processes and sedimentary record formation. The global nature of contemporary environmental monitoring creates opportunities for understanding Earth system processes at spatial and temporal scales that exceed anything possible in previous geological periods. The integration of atmospheric, oceanic, and terrestrial observations provides insights into the coupling mechanisms that connect different components of the Earth system and determine how environmental changes propagate through global biogeochemical cycles. The sediments forming today represent the latest chapter in Earth's continuous record of atmospheric conditions, geological archives that extend the tradition of environmental documentation into an uncertain future. These contemporary deposits will serve as the foundation for understanding how Earth's climate system responds to perturbations, whether natural or anthropogenic, and how the planet's regulatory mechanisms operate to maintain conditions suitable for complex life. The stones continue their patient work, remembering tomorrow's storms as faithfully as they have preserved the atmospheric stories of deep time, writing new chapters in archives that already span billions of years of planetary evolution. The archives sleep now in stone silence, their molecular memories locked within crystalline structures that will outlast continents, outlast species, outlast the very mountains from which they were born. Across the planet's surface, in limestone beds and sandstone cliffs, in coal seams and volcanic ash layers, the stories rest in patient stillness, atmospheric whispers transformed into permanent geological poetry, storms made solid, weather written in the language of minerals and time. In every grain of sand that settles tonight, Earth continues its ancient practice of documentation. The wind that moves across contemporary landscapes carries particles that remember Archean seas, Carboniferous swamps, Cretaceous greenhouse warmth. These traveling libraries drift on air currents that connect past and present, each microscopic fragment containing chemical signatures that span geological ages. The conversation between atmosphere and stone continues in whispers so quiet they can only be heard across millions of years. The formations that preserve these deep time stories stretch across every continent, their exposed faces catching moonlight and shadow, their hidden layers extending into depths where pressure and temperature approach those of stellar cores. Within these buried archives, iron bands remember Earth's first breath of oxygen. Glacial deposits hold the memory of ice ages when the planet wore white robes from pole to equator. Amber preserves actual samples of ancient air, atmospheric chemistry trapped in golden tombs of fossilized resin. Tonight, as sediments settle onto lake floors and ocean basins, the documentation continues. Modern storms leave their signatures in accumulating muds. Contemporary precipitation chemistry finds expression in growing speleothems. Urban atmospheric chemistry settles into river deltas, creating new chapters in archives that already contain the complete history of Earth's breathing. The planet's memory systems operate with the patience of deep time, accumulating information grain by grain, breath by breath, storm by storm. The wind quiets across ancient exposures, its movement slowing to barely perceptible currents that carry dust particles like benedictions across landscapes sculpted by billions of years of atmospheric evolution. In this stillness, the stones hold their secrets with mineral patience, their crystalline structures preserving information about atmospheric storms that raged when the world was young, when the sky held different chemistry, when the very air would be poisoned to modern lungs. Sleep come to the geological archives as it has for billions of years, the eternal rest of information preserved in stone, stories written in chemical languages that speak across timescales beyond human comprehension. The memories sleep, safe in their mineral tombs, waiting for future minds to read their atmospheric poetry, to understand their chemical wisdom, to hear the whispered stories of Earth's long conversation with its sky. In the deepest silence, the stones dream of forgotten storms,